Happy. Ladies and gentlemen, we are about to start. If you can move from, feel free to take the glasses and caps. Jak to máte rádi? Oh. Ready to start, everybody? Good afternoon, ladies and gentlemen. It's an absolute pleasure to welcome you at the Young AI Research Forum 2025. It premiered last year, and given its meaningfulness, as well as the positive feedback we got, we made it a staple of Days of AI, Dny AI. Days of AI has become the largest AI festival in the Czech Republic. This year we are hosting over 250 events in 36 locations, and I'm about to welcome about 15,000 attendees, and thank you so much for being part of it. This year's focus of this forum is on AI as a driver for interdisciplinary research, which is a perfect way to fulfill the goal of this forum. To break down traditional academic silos, spark novel collaborations that merge diverse expertise, and further professional development of young, promising research talent. By bringing together young minds from varied backgrounds, we hope to foster a unique environment for sharing know-how and building the networks needed to unlock new perspectives and accelerate breakthrough in fields ranging from medicine to education. So who do we have in the audience today? How many of you are bachelor and master students? Fantastic. And how many of you hope to continue in academic research? Great. How many PhDs do we have in the room? Fantastic. How many of you do not reside in the Czech Republic at the moment? And do we have any representatives from the industry? Fantastic, thank you. Collaboration is the essential foundation for interdisciplinary research, but it's also essential for organizing this event, which is brought to you by the Czech Institutes of Robotics, Informatics and Cybernetics, Prague AI, which is an NGO with the goal to transform Prague into a formidable hub for artificial intelligence in Europe. Together in cooperation with the Research and Innovation Center on Advanced Industrial Production, the European Digital Innovation Hub at the Czech Technical University, and the Indo-Pacific European Hub for Digital Partnerships. The event is held under the patronage of the Councillor Daniel Mazur of the City of Prague. And we would also like to thank the Czech Ministry of Industry and Trade, which is supporting this event financially within the Capacity Building for Ukraine program. Thanks to this initiative, we are pleased to welcome a delegation of 25 students and academics from the Ukrainian Catholic University and Lviv Polytechnic National University who are here with us today. So what can we expect in the next 4 to 5 hours? An introduction of RICAI by its director, Tilman Becker, and a few thoughts on how to unlock deep tech innovations in Europe by Dny AI from the International Neurodegenerative Disorders Research Center. Next, there shall be a keynote by a world-class scientist, Josef Živec, on AI and in interdisciplinary science. Then we shall have a peek into the worlds of 9 young researchers through their brief presentations. The second keynote will be by Anton and Roman Bushiev on how to start international collaboration in interdisciplinary research, which will be followed by a final keynote of Karolina Pštros, sharing a few useful insights on science communication. We shall conclude the formal parts of the event with the announcement of the first CLARA, acronym for Center for Artificial Intelligence and Quantum Computing in System Brain Research, a Young Innovator Award 2026. Please save some of your energy for networking and sparking interesting encounters and deep conversations. So without further ado, I would like to welcome Tilman Becker and Dny AI on the floor. You have some.
Just try to move to the next one.
Oh, sorry.
There we go.
Here we go.
This is it.
This is it. Cool.
So, welcome on behalf of CTU, and more specifically on behalf of the Czech Institute, and even more specifically on behalf of the RICAPE Center. I'm welcoming you here on our premises of RICAPE, the Research and Innovation Center on, and the AI stands for Advanced Industrial Production, but nevertheless AI is one of the biggest building blocks for the fourth industrial revolution, for Industry 4.0, which is really at the core of what we're doing. RICAPE is a collaboration, not just between the testbed here in Prague, but also with CETEC in Brno, with partners in Germany, in Saarbrücken, at DFKI, the German Research Center in Artificial Intelligence, in SIMA, with associate partners in Ostrava and in Dresden in Germany again at Fraunhofer. We're jointly working on getting AI and digital innovations like digital twins work together to support distributed production and new ways of more flexible and efficient production. So AI as a big component here is maybe the bridge to work interdisciplinary with other fields, because we already have mechanical engineering, electrical engineering, cognitive science, and of course computer science in the lot, and more would always be welcome. So welcome and enjoy the forum.
Thank you, Tilman. You know, actually we have a lot in common with these guys, because you will learn from Josef Šivi's presentation later on that macro world is very well connected with micro and nano world, and I'm looking forward to the presentation. My name is Vít Dočkal, and actually I'm here to welcome you as well. And I'm actually having a question: who is going to who is willing to run a business here? Is there anyone who would like to run a business? 1, 2, 3, 4. Okay, so maybe after this session we would have more entrepreneurs and more innovators coming, and actually this is actually a very important part of this session. So if I may go to my presentation very briefly, because we are already late, if it's there. Okay, the theory and reality of deep tech incubation is very different. You know, it's very easy pathway, but on each step you have obstacles. But don't worry. This is the methodology how to overcome that, right? So don't worry if you see and that you are alone, if you feel that you don't know, if you're really depressed that your solution is not happening, you know, and not doing the things you are actually expecting. This is just normal world, yeah? And why? The next slide, please. Because deep tech is completely different world from a standard commercialization. So it's not that you just do an Uber or something like that, you know. It's more sophisticated. It's drug development, devices, you know. It's completely risky. It's actually starting with a blue sky science. Completely crazy ideas. And we need to actually have the methodology how to shape these ideas towards the market, which is very, very challenging, but not impossible, of course. Next slide, please. What we should consider as a very big priority is to overcome the dead valley. Basically, this is actually, this left-hand side axis is actually the public funding, right? So basically, you get a fund, research project, whatever. You stop here, and you think that you have technology readiness level 6. You might think that, yes. But from the perspective of the investors, it might be 4. So basically, you know, we need to connect these worlds, even in the terminology and expectations. What do you think is technology readiness level? 6, might be 4. And this is actually creating a gap in the ecosystem, which we need to overcome. Of course, the public bodies putting money into that to mobilize the inventions, to create, to actually mitigate the gap from technology level 6 to 7, actually often dealing to mitigating the gap from the technology race level 4 to 5. So the gap still remains. And that's the reason why we are actually excellent in science, in AI, Gen AI, but having only 6% of the market as Europe. You know? Very strange. So we should forget, the standard types, and we should really do something new. Maybe next slide. We really need to run a business. From the first step, we are thinking about the idea. Once you have an idea, a scientific idea, think about the business beyond that. Maybe sometimes it's not possible, so the scientific paper would be better. But always think about that, because if your aim is just to publish a paper, it might be a loss of opportunity. So think of that. And we can provide you guidance and services as part of CLARA, as part of EDIC, and as part of TEF, as part of AI factories, which hopefully come very soon, to provide you services in pre-seed and hopefully in seed funding, opportunities, business coaching, and acceleration. Sometimes you can feel that, the next slide, sometimes you can feel, is it the next slide? Isn't. If you can feel, maybe sometimes you feel that the future is tough, Actually, it's not my invention. It's MIT engine, Maybe let's wait for a while. Yes, this is maybe sometimes your feeling is, but maybe the reality is different. Thank you for that. The future is tough tech, the deep tech innovation. Let's go for it. You are the innovators. Run a business. Make a chance. Thank you.
So I would like to invite the first keynote, Josef Šivec, who is the recipient of the ERC Advanced Grant, wonderful person, who has the Intelligence Machine Perception Group and the Alice Group here at CIRC. He was at Oxford, he was in Paris, and then he decided to come back home. And currently he focuses on teaching machines to understand the 3D world around us. And we are very excited to hear, because he's got some recent accomplishments in actually connecting AI with other fields, how to go about it. The floor is yours.
Thank you very much, Lenko, for the introduction. It's really wonderful to be here. I would like to welcome very much our colleagues from Ukraine. It's great to have you here. And you feel free after the talk to reach out and discuss. So before you run the business, which we just described, you may want to do some research on which you can base your business. And what I will show you in this presentation are sort of some examples of work which is really straddling, and I think that one of the topics is interdisciplinarity. So kind of rather than trying to tell you how to do the interdisciplinary research, we can discuss it also later. I'll try to show you by examples, like examples of what we've done. And I will start with the background more sort of on the boundary of computer vision and robotics, but then also you'll see that similar techniques can be also applied in the world of molecules. And it's the theme is about physical interaction, as you will see, is to either on the macro world and in the sort of molecular world. And I need to make sure this works. Yeah, as kind of my background here, I started as a bachelor and master student here this building wasn't here, but it was sort of in the building across the street. But then spent more than 15 years abroad, and then came back here and, as Lenka said, so running a team on doing machine learning for robotics, computer vision, and protein engineering. If you think why computer vision is interesting or important, have a look at this picture. So at the moment, machines like robots, they are equipped with cameras which can sense the world around us. we can see the visual sensors here, but they also have actuators, the hands, which can interact with the world. Like here, the robot from Boston Dynamics is actually holding a piece of wood. And so they can sense the world around them, interact with it, but also, and I think that's a very sort of important to understand, so when they do the interactions, because they have the visual sensors, they can observe the outcome of these interactions and learn from these outcomes. So computer vision is really a key component of these future intelligent machines, which will be able to observe the world around them, interact with it, and learn from these interactions. Now, for a moment, imagine we did really have machines which would have the similar capabilities as humans do in manipulating objects, using tools, achieving complex tasks. It would be really a revolution in manufacturing. Not only that, the machines could go to places which are dangerous for people, for example, or teach humans how to do things which they don't know, teach novice users. And not only that, imagine, so we had really seen like the revolution in diagnosis, medical diagnosis, and we discussed some of it earlier today. But imagine now we have machines where machine learning is enabling to be actually better at almost any single doctor, because it can pool information, can learn from many different doctors to diagnose people. But now imagine that we could have this revolution also in surgery. Imagine that these machines could actually learn. We don't have that yet, but they could learn from doctors, but also they could sort of learn how to perform surgery with new levels of accuracy and robustness, potentially better than human surgeons. So we don't have quite these techniques, these machines yet, but what we do have, we have amazing chatbots. So many of you have probably used tools like large language models, which have quite amazing ability to manipulate and work with natural language. So I use this example. This is from GPT-4, and this is performance of some of the sort of standardized tests. And the one which I typically show is the uniform bar exam. So this is a legal exam which you have to pass if you want to practice law in the United States. And the GPT-4 system not only passes it, but it passes it better than 90% of humans. And there are some other various other standardized tests. And so, but these systems, they're one of the key part of them, or why they work so well, as we've seen because of the scaling. So they have this amazing number of parameters, like this GPT-3, the previous version, had hundreds of billions of parameters, and they are trained on really hundreds of billions of words. So just the computation here is, which equals about 2 million books. And there's GPT-3, of course, now it's orders of magnitudes more. So we've seen that, they have this scaling and lots of data to make this happen. Together, of course, with infrastructure which are they trained on, and new class of algorithms. So at the same time, so we have these machines which can manipulate natural language. At the same time, we don't have a machine which could reliably empty a dishwasher at our home, or which would have the abilities of manipulating objects in the kitchen as a 10-year-old human. Yeah, so my 10-year-old in family, I wish she could do more in the kitchen, but of course we don't have any machine which would have a similar level of capability. So you may wonder why that is, and of course, surprisingly, or maybe surprising for you, but it's not new. So this has been already observed in the 80s by researchers in machine learning and AI. And the one particular person I've shown here is Hans-Peter Moravec. He was of Austrian origin, working in the US, and we call that since then Moravec's paradox. So he said it's relatively easy to get computers to do intelligence tests or playing checkers. So these were the kind of sort of abstract tasks which the machines could do at the time very efficiently. But when it comes to perception and mobility, it's difficult or impossible to give them the skills of a 1-year-old child. Of course, the research has progressed since then. We have machines which are better at the perception and manipulation, but of course they are far from human, far from people. Of course, we don't quite know why that is. I mean, he had a hypothesis which was related to evolution, that the visual motor skills have really evolved through animals and through evolution through billions of years, whereas the abstract thought, as he said, is a new trick, perhaps only 100,000 years old. So we don't quite, we don't know for sure if this was his hypothesis, but what we know from practice is that one of the key enabling factors was the amount of data, which we show in the language, scaling up the models, the model sizes, and the amount of data. So in the sort of robotics or vision and robotics community, so now there is this quest of getting, where could we get? We don't have that data in robotics, and it's not as easy. You can't just go go to internet and just download lots of robot data. It's just not there. So, so there is this quest in the community of getting, how can we get to the levels of data which we see in, say, in natural language. So I will structure the rest of the talk around some of the key directions which I believe are interesting or promising to get the data. And now you will see that I'll show the parallel that actually also in the molecular world, we can sort of take some of these lessons, and also we have actually similar problems with getting the data and maybe similar strategies. Gardening, cooking, or even health. So this is a wonderful resource where we could potentially use to teach machines how to do things. So it's one source of potential data, very different visual and in natural language. So imagine, wouldn't it be great if you could take this data or video like this and extract from it some kind of instructional manual which we could upload to a robot and do the task in real life. Of course, we are far from this at the moment, but we are making steps in that direction. So this is an example of work where we take a YouTube video as input on the left and then extract a trajectory in 3D of the motion of the person manipulating the tool. So you can see the person and the tool, and the yellow arrows are actually interaction forces between the person and the tool and the ground. So you imagine, well, why do we do that? So this is an example where we can take the same another instructional video and use the video to teach this motion to a robot. So this is a difficult task. This is a dynamic motion with shadowing. So we developed a method. And as you see, this is a kind of combination of extracting the motion. And I will go a little bit of detail so that you understand what's behind that. Yeah? So I'll show a little bit of detail here and there. So in this case, one of the key components after we extract the motion from the video is formulating this as what's called a trajectory optimization problem in robotics, where the goal is to so there's a loss function, it's an optimization problem, where the goal is to obtain the trajectory of the robot. So this is here over time, together with the position on the robot. So this is what we optimize over. And we have a loss function, which is over time here. And it's some of different terms. One of them is how well we sort of imitate the motion of the robot from the video, together with some constraints on the speed and respecting of the joint limits. Of course, the robot cannot do something which is not designed for. And we can solve this problem using as an initialization for additional reinforcement learning formulation to refine that motion and transfer it onto the robot. So it's a combination of optimization and sort of learning, and we sort of we use for these tools developed by colleagues in France to solve this problem. And I'll show a few more results. What's interesting that this technique works for different robots with different degrees of freedom. As you see here, even for a humanoid, which you see at the bottom, and the results are in this case in simulation. There's, I think, something happened with with the slides. Hello. I'll have to go back a bit. Okay, so I think I'm back. So, yes, you're not. Okay. So this we've seen. Right, so at the moment, what you've seen so far was really manipulating the tool, which was like a stick, like a spade, for example. But we also looked at how to generalize these techniques to 3D objects. So this is an example of an input from a YouTube video of someone manipulating a can together with a 3D object. And here the problem which we try to solve is estimating the pose, relative pose of the object with respect to the camera. So this is the 3D object, this is the image, and this, we try to estimate this transformation. It has 6 degrees of freedom, 3D for translation, 3D for rotation. And what's interesting is that, and I will show... I don't know, is it related to this or? Okay, so I will somehow we need to. Do you have another clicker or this is it? Okay. We tried everything, but didn't expect the clicker is not going to work.
You can just give us a signal and we will...
Or advance the slide, yeah, but there's sort of many... okay, I will also use the opportunity to maybe speed up. So I will show it as just an example of the second way how we can get a training test actually simulate, learning from simulation of the real world. But it's a difficult problem. It's a very hard problem because of just the sheer variability which we see in the world. It's not easy to simulate, but there are examples if we constrain the problem enough that we can actually simulate. And one example is visual data. We can actually, this is all synthetically generated training data where we have thousands or tens of thousands of different objects which we can simulate, put them on the ground, and we know everything about the scene and use it as training data to train such kind of models which can estimate the pose of the object given a CAD model in the image. So it's again a large neural network which is trained from the synthetic data, which sort of iteratively refines the sort of pose of the object, estimates it, so that and I will show as an example what the output looks like. So given an input video, we can then estimate the pose of the object relative to the camera and sort of track the object in 3D. You may say why this is useful. And exactly because we can use it to gather training data for the robot. So at the bottom left, you have input video, you have estimates of the robot motion, of the 3D motion of the object, which you can transfer of the robot and use it to teach the robot to do specific motion. You can see it has these fine details of the motion, which would be otherwise hard to reproduce or program automatically. And of course, we are looking at scaling this up. This is ongoing work where we can scale it up to really arbitrary YouTube videos so that we can extract the motion of the object and transfer it onto the robot. And for this, we've collected even a data set of sort of more than 1 million YouTube videos of the different instructions and sort of are looking at ways how we can collect large-scale robot training data from this. And I'll just to appreciate the sheer variety of what people show on YouTube, and I think if we could have it as a way to, and this is examples of the robot trajectories which we can extract from this data, and I will maybe skip this. It can also be used, the data, for actually also skip. You can also be used to pose this mission on a robot. What I want to say is more about the limits of current hardware. So while our human hand is amazing actuator, we can interact with the world, we still don't have quite the level of robot hands which would have the similar capabilities. And at the same time, we have huge limits in what the simulation can do. And that's why we've also developed techniques which don't quite simulate explicitly the physics, but they can learn to simulate the physics. And here is an example so it's especially important if you want to, say, manipulate food or do things which are deformable or we want to cut things. We don't generate full video, it would be too expensive. Even the best models can't do that type of length, but we can generate keyframes, which is already interesting. And we've developed a new model which allows that, which is special temporal attention. And I will sort of conclude this part about robotics, about this learning from other machines, which I think is really one of the key open components which will help and enable this. And they are already beginning, so the different groups, research groups are beginning to store and collect and store data for different robots and share it among them so they can learn from each other. But what I think will really make a difference once we have really the robots which can learn their own local models by interacting with the world, and we develop new techniques which allow us to not share data but share models. So I think that's something which we are working on. It is a very much open problem, but I think if we do enable this, we will have a sort of much better capability of scaling up the robot learning. And then the sort of second part of the talk, I want to show you that we don't, by this illustration, this video, so you may think, well, what kind of robot is that? But the fact this is not, this is actually a protein. So this is a protein called kinesin. It's a motor protein which does transport sort of material inside a cell. It's sort of attached to it and then can sort of move it around. It's called the motor protein. And I think many of you have seen now quite a lot of examples of proteins, so I'll try to go quickly here. So proteins are very important components in the human body. This is a slide from Petr Koba, which is very nice. It's not just a nutrition. They are really enzymes in the human body. They are drug targets. They can kill disease. They can kill viruses. But what's interesting that despite the fact, and there's all this progress, there is still we know actually very little about the processes in the human body. So just in the human brain, it's more than, I think, 10 or 20,000 different proteins and hundreds of different small molecules. And we understand very little about the processes. And I think it's a huge opportunity for machine learning to help us understand these processes better. And you may say, why is that interesting? And one important application is to cure disease. I'm showing two diseases which are related to brain, which is the topic of the CLARA project. Alzheimer's disease, a huge impact, seventh leading cause of death, and we don't have an efficient drug for Alzheimer's disease at the moment. Another one is acute stroke, and here there's a great need for a more efficient and inexpensive thrombolytics. And I will use those as examples of where sort of machine learning could help us. And what's interesting is I think the story about the data is very similar. So the data really is one of the key limiting factors for the machine learning techniques. And but here we can use a similar sort of directions how we can go about gathering more data. The first one is learn from existing data we have about nature. So we are, for years, have been measuring, or different labs around the world have been measuring, say, about data, say, about proteins. And we can use it and train from those data. And this is an example of a work which I'll try to, will not go, don't have time to go in detail, by Anton and Roman Boucher, who are also here to talk with them. I'll show pictures. You can try to learn to distinguish them from these examples. It's about designing or learning to design protein-protein interactions. Just as an example, so this is a protein called staphylokinase, which is used to treat stroke. So it's a candidate drug to treat stroke. But so for stroke, there is a fibrin clot in the in the brain and which we want to dissolve. And this particular protein works by, this is the drug candidate, staphylokinase, and it works, it's a kind of a chain reaction. It forms a complex with the plasmin, and this complex further breaks plasminogen into more plasmin, and this way kind of feeds back and makes the sort of breaks the clot faster. And what we would like to do in this project was to look at this plasmin staphylokinase complex and optimize it. And optimize in particular, we've been looking at how well these two proteins bind together. Just in case you haven't, for those who haven't seen it yet, so proteins are really that are built from these 20 different amino acids. These are the building blocks, and they form these from the sequence. They fold into complicate like this complex 3D structure, and which we see here on the slide. And sometimes you see this structure visualized using this type of visualization. And in this particular case, we have the complex of the two proteins here, the drug candidate and the plasmin, and we would like to, they have this interface here, which you see a close-up here, and we like to optimize the interface so that these two proteins bind better together, and chemical reaction, but it can take hours or maybe sometimes more to compute. So the idea here is to design a machine learning method to do that. Before I go into this, say more about how to quantify this attractiveness of different proteins. This is done by what's called the binding energy, delta G, and you can think of it as what's the energy when the two proteins come together, how the energy sort of gets, it's lower, it's a better energetic state, so it's typically negative if you want to, or would be the energy to take them apart, these two proteins. So the lower is better, and what we are looking in particular at is what's called the delta G, which is the change of this binding energy, delta G, upon the mutation. And the goal is to sort of predict what would happen if you do mutate the protein, change the energy. Of course, you can set it up as a machine learning problem where you have data set, in this case, 300 interfaces, 7,000 mutations, and you observe, you have measured data, what would be changed of this binding energy if you do this mutation. The problem is there is very little of this data. It's about only 7,000 data points, which is not very much. So the very nice, so this one way how to approach it, the idea is to actually do large-scale unlabeled data, which is the idea here of Anton, and collect from the existing databases of proteins and the complexes, collect interfaces. So the data set Anton collected is more than 300,000 these interactions, and which can be used to generate millions of examples. And really the idea here is coming from the natural language. If you have a sentence, you can mask a word and have it to predict it. That's how the language models are trained today. But the idea here is to apply it on proteins. Proteins here are modeled as graphs, and you can where the nodes are individual amino acids, and the edges are the sort of modeling the chemical reactions or relations, and the bonds. And here the two dark ones are masked, and the goal of the model is to predict these masked amino acids, similar way you would predict in language. And this way one can learn a model which can be then, I will skip the details, which can be fine-tuned to do a this delta G prediction, and it works better than some of the other techniques. And I will skip all the details of the model. I'm happy to discuss them later. One can validate the technique on standard data set and also show that the different components of the model improve the performance. And also that it's important to do this pre-training the mask modeling. So when you do the training, it is sort of with the pre-trainings, the red curve, it sort of learns a better model which better correlates with this delta G energy. And so Roman and Anton, they have done this very nice demo where a biologist can go and try this model on their data. They just input what proteins they're working on, what amino acids they want to change, and the model will predict what is the likely change in the binding energy. And what's interesting is that in the end, like the ultimate validation, of course, is in the wet lab. So I think it's an example of actually mutants in our colleagues in Brno in the freezer, which are sort of results that are sort of designed based on the model predictions from Anton have been later or tested in the lab. So I just want to give you, so this was an example of when we use existing training data or existing data and train models from the existing data, which we somehow manipulated or used it similar like in language, but in this case in mask modeling. You'll saw more examples in the following talk by Antoine and Roman. Again, I show you pictures, you can guess who is who later, in this domain of training from existing data. But of course, there are sometimes the data is not accurate enough, or we just don't have the relevant data. I think there where, again, the simulation comes in. And here is an example. And what's interesting here that the simulation can be quite accurate in some situations, but is usually very slow. So there's an example of modeling interaction with a small molecule, like a drug candidate, with a protein. And there are some examples of computed energies, and this computation, as you've seen from the talk of Saltuk earlier today, is some of them they can take hours, sometimes even days to compute. At the same time, we can then use this data to train the machine learning model, which can perform much faster. So I think it's a potential, a huge opportunity how we can sort of potentially even iteratively train a machine learning model from simulated data. The example here is really, and some of you have seen the examples, I will not go into details, the ApoE protein and modeling the interaction with the small molecules. It is a protein which is key, one of the keys, we believe, to the Alzheimer's disease. And it's exactly here where one can use the sort of simulation, accurate by slow simulation, to generate training data. And it's exactly what we are looking for at the moment to potentially even find small molecules which can modify the behavior of this protein. And you've seen some earlier that these are examples of these simulations. So I think we can train models from existing data, learn from simulations of nature. But I think really the ultimate goal is to even have the machine learning models interact with the nature. And I think this also is a fantastic opportunity where, and I think that's where the future, I've discussed a little bit yesterday, lies, where we have a physical simulation of the bioprocess, which we can use to generate training data, to feed in the machine learning model, and the machine learning can design, experiment, or suggest, say, which mutations to test, or what kind of experiment to execute in a experimental robotic biological platform, and then collect data and then feed it back to the physical simulation and the model training. And then in this loop, can really sort of achieve or find sort of answers to questions which we have in a much faster manner, because we can optimize this loop and it can operate in a basically much faster. I'm showing it here because our colleagues at ICRC in Brno are getting one of those machines. Things should be installed this year, and we are already now thinking how we are going to use that in this kind of a loop to sort of find results to some of the scientific questions which have in a much faster manner. And with this, I will sort of conclude. I think at the moment it's really a very exciting time to be here in this area where we are sort of in the researching intelligent systems that can interact with the world and help us understand the nature and the processes in the nature in the human body. I think it's a long-term process. It's not going to be here next year. And the reason is that exactly we don't have the data which we can just download. We kind of have to sort of work together in different ways to collect the data, to simulate and interact with the systems. So that's the limiting factor is the fact that we have to interact with the physical world to collect the data. That's why it's going to take some time before we can have the protein ChatGPT, which would know all the answers to what's happening in the human body. Yet, I think we're going to have exciting things happening along the way soon. We'll have robotic systems which help us to do difficult things like farming, or we have new drugs which we're going to discover on the way. I'm trying to work this. And of course, I would like to thank very much my team, my students, and postdoc. It is science, it's a teamwork. It's really their work, so I'm happy I can tell you about this here, but it's their work. And it's a interdisciplinary teamwork, in fact. There are pictures from a joint workshop with colleagues in Brno, where we have to go. It's an expertise in different domains we require to tackle these problems. We have to really sit down and talk about it. So it's not, and work together. It's not, we can't solve it alone. That's why it takes additional work, but it's very exciting. There's another picture from another joint workshop between machine learning and biologists. And finally, one key missing component in this, which you may, which I would like to mention, is that, I don't know if this, the most important component may be, it's you. So in the end, maybe here sits, someone who is going to do research and who is actually going to discover the drug for Alzheimer's disease. So I'd like to mention here the different opportunities. I know that some of you are looking for doing master thesis, maybe even in different countries. So I do mention here the Prague AI Master, which is a new master program here in Prague. There is ALICE, which is Pan-European initiative, has a PhD program. I've discussed with some of you that, you're bachelor students, so you're looking for master programs. This is an example for our ALICE unit. You can click go. I think the slides will be online. You can check. We have some thesis topics, but many different ALICE units around Europe have also master programs and topics you can go. I just mentioned few here: Amsterdam, Tübingen, Munich, Zurich, and us. But Paris also has a fantastic master program. So, go apply for them. And thank you very much.
Thank you, Josef. I have one question for you. I forgot to mention. Those with the blue name tags, consider yourselves lucky because there's a QR code that is leading you to Slido through which you can ask questions. So please use this opportunity, otherwise I will have to ask all the questions and you don't want me to do that. But I do have one question for you, Josef. Are there any soft skills you believe are quite critical for successful interdisciplinary collaboration?
I was thinking, I also wanted to prepare a slide, what is doing interdisciplinary collaboration? So I think in this experience, I think your patience maybe, because the first year or two, we just had to find common vocabulary. What is a protein? What is a ligand? How this works? So it requires a lot of kind of communication. But what was surprising for me was that the kind of doing good science, like design experiments, changing one thing at a time, the understanding. I think that's maybe really that's the most important in science, is the quest for understanding. You really want to understand what's happening. And I think that seems to be common with the biologists I work on, where we find the common chemistry, is that this quest for understanding. So maybe that's it.
Thank you. Okay, and before we let Roman and Anton impress us with their results, we would like to invite 9 promising researchers from the Czech Republic as well as Ukraine, so they can not only show off their research, but also practice their presentation skills. So the first in line is David Beinhauer from the Faculty of Mathematics and Physics, I believe, from Charles University, who is going to tell you about his experience from bridging the world of computer science and biology. The floor is yours.
Okay, so good afternoon, everybody. I would like to introduce you quickly into the research that I have done throughout my master thesis on the topic of modeling visual cortex using kind of biologically inspired deep neural network models. So, first of all, what was the motivation of the whole study? The brain itself is a large, complex computational system where a lot of nonlinearities are present, where a lot of recurrent connections are. And the result of it is that the system is highly changeable, highly dynamical, and in the practical usage, if we want to understand what happens in the brain, we also need to understand this dynamics of the system. So this leads us to two state-of-the-art approaches. How do we currently study the brain? First is based on the differential equations, where you simply define the behavior using differential equations. This approach works quite well. However, since we don't understand the system perfectly, we also cannot define this equation perfectly, and there is definitely room for improvement in the modeling task. So what might be one possible optimization is to try to replace deep neural network models in the step where we would like to train the deep neural network models to define these differential equations instead of us. This approach is also proven to work quite well. In fact, it sometimes outperforms the previous approach, especially in predicting mean neural responses. However, in the task of predicting fine temporal responses, it still lacks in comparison to the previous one approach. And furthermore, since a lot of deep neural network models are designed as some form of the black box, we are lacking important information about the interpretation of the problem. And since we want to really understand what happens in the system, we would like to also try to explain what happens in the model. And with this idea, we get to the topic of my master thesis, where we try to conduct the proof of concept research, where we have taken biological data, in our case only the artificial one generated by the model based on the differential equations. We generated these data, and we tried to use them as the training data to train the deep neural network model, in which we developed the way that the architecture that we aimed in the architecture that there will be one-to-one correspondence in the artificial neuron and with the real-life neurons, and where we applied large amount of biological constraints. So, for example, we differentiated between different neuronal populations. We differentiated between different neural connections. And what are the results of our study? In this slide, I'm showing you the mean temporal responses in different populations of the neurons. In the first three lines, I'm depicting three different models. The first one is the least biologically constrained, and as you can see, the predicted neuronal responses doesn't really fit well the target ones. The model predicts quite well the mean behavior, but in the temporal resolution, it still lacks. But for example, in comparison, in the third line, I'm showing the results or the predictions of the model where we include the most of the biological constraints. And as you can see, the temporal behavior or the predictions in the temporal manner are almost fitting the target responses, which might indicate that the more biological constraints you use in the deep neural network models, the better modeling properties you get if you want to model the brain systems. And in the last line, I'm also depicting the behavior of the model where we included only a few hundreds of neurons. Why we have done this? Because in the real-life experimental results, we can get only a few hundreds of neurons. And so we wanted to try what happens if we include only few of them, only this amount of them. And as you can see, the temporal resolution is also quite impressive. It almost quite fitted the target data, which might indicate that this approach might also work in the real-life experimental data. You would be able to enhance our understanding while using only the real-life recordings. And this is it. What might be the next steps? The next steps might be finally trying to apply this approach on the real-life experimental data, and then ideally to extend this model. And this is it from my side. So thank you all for your attendance, for your attention, and thank you.
I cannot see any questions on Slido, so I have a question. Oh, fantastic. Okay. I shall try to use this if it works.
Excellent. Is this on? Yeah. Excellent presentation. Thank you. In your results, I noticed that when there was this stimulus change towards the right-hand side of those graphs, the models weren't doing such a good job as matching the target. I just wondered if you could sort of speak to that. Is that something that you're hoping to improve upon going forward?
Yeah, definitely. I didn't explain because I didn't have time, but yeah, the task was basically that we have shown the picture for some time period where was the first stimulus change. It was like the first reaction on it. And then we changed the stimulus we were just removing the image and showing only the blank image. And in fact, this is the drawback of our model, that we are still not able to really capture the later predictions of the neural dynamics when we are presenting like no stimuli. We are lacking the kind of constant neural activity in the model. Yeah.
Very interesting presentation. Tell me, did you use only RNN or LSTM or GRU?
Yeah.
Did you try?
Yeah, the architecture was quite complex. It was like the outer RNN, like the classical RNN, but within the model we had the shared modules, which was created from the LSTMs, especially in the the most biologically constrained one. We used LSTM instead of neurons and instead of neural connections to simulate the the connectomics neural depression or like the neural adaptation on the stimuli. So we used LSTMs as a small modules, but the outer kind of network was just typical RNN. Yeah.
Okay, thank you.
Okay, thank you so much, David.
Thank you.
The next in line is a representative from the dopamine team. Fantastic, thank you so much. Combining immersive learning from Ukraine. Somebody coming? Sorry, this is what happens when you don't put your name into your presentation. Combining immersive learning with entertainment to help patients with neurological traumas. The floor is yours.
Thank you. Hello to everyone. I do not have a blue badge because I am from the old school. I'm not young, but doesn't matter. We would like to present our emotion platform, which we use and try to use in different kinds of solving issues. So first of all, this idea was appeared when we tried to create some new feelings from entertainment. Also, we tried to use it for education, for using this modular simulator in different kinds of vocational colleges and schools. And the third, which I will show in the next slides. So our modular simulator has different kinds of degrees of freedom from 2 to 6. We can use it for transform or transfer you to real feelings in aircraft, any kind of vehicles, or etc. So the first way is education. A lot of our schools cannot afford different kinds of very expensive technical or any kind of vehicles. So we can use it, and we already delivered and installed 2 of these platforms to our vocational institutions and educational centers. So also entertainment, and we already also installed and placed 3, I think, these modular systems for entertainment in our sim races clubs for gaming, etc. And then third, maybe the main, which we are trying to help our veterans to recover, is exactly recover their brain and any cognitive activity. And we already test it with Unbroken Hospital in Lviv. We also installed this model simulator for rehabilitation our veterans from any kinds of injuries of brain and post-traumatic stress disorders. Market opportunity is very wide in these different kinds of markets and not about all. Our way from the start, from idea appeared, it just appeared in 2023, and we went a lot of way, different kinds of pitches, contests, and etc. So now we have different points of TRL, or technology readiness levels, in our different kinds of degrees of freedom platform. Our team, it's not constant. We always add some experts from any kinds of branches of these our three or others interests. And unfortunately, here it was a video, and you can see how we use it in these our three ways of using. I hope it will work. Or maybe no. Oh, yes. You can see we use a brain-computer interface on the head of this veteran. He does not push on the acceleration, and just from the brain waves he can control, for example, accelerating of this machine. And after concentration, after these brain waves, we have opportunity to involve our veterans without legs to control and try it for recovering, also for brain recovery injuries, from injuries. We tried to use in different kinds of ships, aircraft, cars, special equipment, or some cars. You can see the person doesn't push on the accelerating and the car is go. You can see this also. Please, could you please help me to push the next slide? Oh, it's not wrong way, sorry. So in the end, I want to express our special thanks to all people, also from Czech Republic, who help and still help our people, our nation, from our defending from our enemies. Thank you also for inviting us to here a conference, also for opportunity to share our experience, to gain new knowledge, and to transfer to our country. So thank you very much. Slava Ukraini!
There is one question for you. Can it be driven on roads?
I'm sorry?
Can it be driven on roads? That was the question.
I didn't get it, sorry.
Can it be, I don't know. Can it be driven? Who asked the question? What do you mean by the question? Anybody who asked the question?
Чи можна так їздити по дорозі, наскільки я зрозумів?
You mean for using this platform?
Mean using this platform on road or what?
No, just you just gain experience like exactly in the car, in the cockpit. Your chair is moving when your car is accelerating or turning.
It does.
So I answered for your question?
Okay,
Thank you.
fantastic. Okay, thank you very much. The next in line is Martin Krucký from the Department of Computer Science at the Czech Technical University, who is going to share his latest research on explainable AI. Please go.
Okay, yeah. I will not be as technical as the speakers that you heard before me, but I will share some high-level overview of this topic of evaluating or assessing explanation techniques. So just a quick overview. We will first talk about the explanation in the broadest sense, the big picture of explanations, why we need them. Then I will quickly talk a bit about the range of techniques that we use in our initiative. Next, I will try to tie explanations to the topic of responsible AI, so why we need explanations to develop AI responsibly. And finally, I will do a quick shameless plug of our initiative. Yeah, so let's start with the big picture of explanations. A question that I always find whenever I come into some technical audience is, do we need explanations at all? Isn't it enough if we have AI systems that are just accurate enough? And maybe from the title of the presentation, you understand that my answer to this question is, yes, we do need explanations. And the motivations that I decided to select for you today are these three topics. So firstly, responsibility. Obviously, AI systems cannot be responsible by themselves, but AI systems nowadays are often complex systems consisting of multiple models. So without explaining how does the model work, how can we assign responsibility? This is also a good opportunity for you to work with ethicists who will help you put up the norms by which you should assign the responsibility to concrete people. Second topic is improvement. So when we manage to use all the low-hanging fruits coming from scalability of current models, how can we ensure that we can correct deficiencies in models? And final topic is regulation. Yeah, so you may have heard about some regulations like AI Act or some other regulations, maybe in US or other countries. So without knowing how the model works, without knowing how the decisions were made, how can regulators actually fairly audit the models that are in front of them? So these are my arguments for explainable AI, why we need it, even if we have accurate models. Now, very quickly, for some few techniques. So, in our initiative, well, you may be you may know some of the explanation methods stemming from attribution techniques, but in our initiative, we have knowledge of explanation methods, everything from counterfactuals to mechanistic interpretability to different neurosymbolic methods. What we have learned is that there is no single best explanation. And instead, you have to always choose the best explanation that is best for the current application at hand and the current status. This brings me to the third section, which is why are explanations necessary for responsible development of AI? And for us, what is most important is the motivation behind European regulation called AI Act. And based on that, we are developing, still actively developing, and we will be happy for any feedback on this, some kind of assessment framework that helps you decide which of the explanation properties are most important. So on the left side, you can start from the AI Act, from the classification that of your potential AI application, how the AI Act sees it, and from the right side, you decide which kind of audience or which kind of stakeholder, from which point of view are you looking at it. On a on a concrete example of automatic exam proctoring, where the system is trying to detect possible cheating, you can see that AI Act would classify this AI application as belonging to education, and this would highlight the properties of intuitiveness and faithfulness of the explanation. On the other hand, if you see it from the point of view of a subject, then you might also add the properties of verifiability and robustness. That's basically it. I hope I at least partly motivated you to work on this interdisciplinary point of view of explanations, either by yourself or please come join us. We are this Responsible AI initiative meeting almost every Thursday at Charter Square.
There's one question. What are the arguments that support the idea that we do not need explanations?
Yeah. So I hope I will not make it sound too naive, but basically that well, if you have a system that is working currently with human operators, you can quantify some accuracy of the human operators, and then if you are able to quantify that the AI system is doing better in the accuracy, then you can just deploy it. Why would you ask about the explanations of the AI system, right? Like if it's better, then we do not need to ask what is happening behind. But so sort of this is the argument behind that. And, well, the three properties were kind of my response to that.
Thank you. Thank you very much. So the next speaker is Šárka Lísková from the Department of Cybernetics at the Czech Technical University, who is going to share her latest discoveries in bio-inspired active vision.
Thank you. Okay, good afternoon, everyone. My name is Šárka Lísková, and I will be talking about our current project on bio-inspired active vision. Okay, so I'm currently a PhD student at the Faculty of Electrical Engineering, where I joined the Neuro-Inspired Perception and Cognition group, which is led by Assistant Professor Giulia D'Angelo. Well, now, imagine you are taking a work call and your robot brings you a nice warm cup of coffee while also cleaning your apartment and maybe managing your calendar. All of that in unconstrained environment and with minimal power consumption. That sounds like sci-fi, right? Why don't we have such robots nowadays? Well, the robots we currently have are clock-driven. They have small internal clock, and each time this clock ticks, the robot needs to check all of its sensors if any of the values changed. Now, that's how it perceives. Not really efficient, right? So how do we humans do that? If something touches my hand, the receptive field in my hand will send this information immediately into my brain. And if nothing happens, there will be no signal. We are event-driven, and thanks to that, as I'm standing here talking to you, thinking about the next slide, my brain consumes about 20 watts. That's less than a light bulb needs. That's impressive, right? So let's take event-based sensors and put them on our robot. Now we have our data. We could process them with CPU or GPU, or we could take it a step further and process them with a brain-like computers. We can do that if we pick neuromorphic hardware. Those are special boards with small circuits, each emulating what a biological neuron would do. So they get input in form of current spikes, and the neurons only react if their membrane potential exceeds a certain threshold. Then there will be output of 1. Otherwise, there's 0. So this whole system computes with ones and zeros in continuous time. Now, if we combine event-based sensing with neuromorphic computing, we can build systems operating with microsecond latency and milliwatt power consumption. Can we apply all of this to vision? Yes, if we use what we call event-based cameras. Those are inspired by how our retina works. Each pixel of this camera gives you an output only if it detects a change in light intensity greater than a given threshold. Then there will be an event. It is defined by its XY position, a timestamp of the exact time, and polarity telling us whether the intensity increased or decreased. So we get this flow of dots in continuous time, and we can process it using the neuromorphic platforms behind me. Now, those cameras are highly reactive, so if the camera was moving, meaning the whole scene would be moving relative to it, there would be lots of events. We could process them all, or we could ask the nature how to do it in a smarter way, because we humans, we don't process all of the events. We focus our attention, and our vision is active. The attention actually comes from how our retina is built, because there's just a single spot where we see with the full nice resolution, and in the rest, our vision is sort of blurred. So in one time point, we never actually see the full scene nicely. We see the spot with high resolution and downsampled periphery. So to make sense of the world, we need to move our eyes. We need to explore. And as we do it, we need to make sense of how the visual sensory input is connected to the motor action, the motion of our eyes. So it's sensory motor exploration. Now to the project I'm working on. So we are trying to get inspired by this little guy here. He's sitting there, playing with the ball, exploring it, and eventually it will get the concept of the ball. It will learn what it is. So that's what we want to achieve with our agent. It has event-based vision. It can move its eyes to observe different points of the object and also rotate the object as well. At each time point, it sees just a piece of the scene with the downsampled periphery, and this input leads its next action. It's the eye movement and or rotation. So as it explores through time, it actually builds a sequence of sensory input and motor actions. Now, the challenge is how to put all of this together into some sort of working memory, which could give us a single representation of the object. So that's what I'm working on, and currently I'm exploring how we could use something called vector symbolic algebra to do that. That's a mathematical tool representing data in high-dimensional spaces. And the nice thing is we can represent both continuous and discrete values of different modalities and put them together. So we could put the visual glimpse, the patch, with the motor command and with the timestamp together, and then represent them together in time using, for example, exponential moving average to simulate forgetting of some sort. Another nice thing is that it's compatible with the neuromorphic computing, so we could count it on those brain-like computers eventually. The bigger view is to put this onto iCap. It's this humanoid robot from Italian Institute of Technology, which we happen to have in our lab. And given multiple objects, it would observe them, explore them, learn them, and eventually classify them with little data and minimal power consumption. So that's what I'm working on. Thank you for the attention, and if this sparked any ideas on how to improve this project, please let me know. Thank you.
Is there a question from the audience? I have a question for you. Oh, there is. Okay, fantastic.
Maybe your question is better. I don't know.
No, go for it.
Really nice talk. Thank you. Super interesting. This is maybe out of scope, but as you were describing the problem statement, it seemed to pertain to, like you said, the young child seeing something for the first time, exploring and manipulating and seeing it from all angles. But as adults, when we see a banana, we don't have to visually explore it and turn it around. We do the pattern matching piece. So we have that representation already stored. And so from the imperfect retinal view that our brains actually see, that's not what we perceive. We perceive the full 3D banana because we have the pattern match.
Yeah, the movements are super fast. We don't even know that.
Yeah. And so I'm wondering, are you sort of the next step to your project, or maybe, I don't know if it's in scope for your time there, or it will be someone else, is building up that bank of experience and the pattern matching, so you don't have to de novo explore an object when you see it a second time and a third time?
Yeah, exactly. The idea is that the next time you just need really a small amount of data, just a few glimpses, and you know what the object is. We want to build some sort of invariant representation through this scanning and then use it for that. Thank you.
Thank you very much. So the next in line is Mikhailo Buleshny from the Ukrainian Catholic University, who's going to enrich you with his research on constraint-aware learning.
Yes. So, hello everyone. My name is Mikhailo Buleshny. I'm still finishing my bachelor degree in computer science. And I won't say that it really resonates with previous work because my research falls directly in the domain of neurosymbolic AI. So my topic is constraint-aware learning of probabilistic sequential models for multi-label classification, and our goal is to change the view on neurosymbolic problem. So let me first introduce the problem we try to solve. We try to solve constraint multi-label classification problem, where multi-label classification problem is a problem where each data point is associated with a set of possible classes. But because the real world is more complex, not all combination can be valid. That's why we have to introduce the constraints. And that's a constraint multi-label classification problem. So on the right side, you can see an example from RODA, our dataset, very famous dataset for neurosymbolic AI, where each bounding box is associated with a set of classes. And of course, those classes have to satisfy the constraints to be meaningful. And so yeah, those constraints can be expressed in our case, it's propositional logic form, like implications, exclusions. And I also have an example of violation that where a model for some reason violated the constraints and produced red and green traffic light at the same time. And of course, this can cause some very terrible consequences. So there are many different approaches to actually tackle this problem. So one of the most famous is, one of the most obvious, I would say, is just a small post-processing approach where we just correct the output to make it consistent with the constraints. But there are also very sophisticated approaches like CCN that actually integrates a special layer that is differentiable and allows to train a model together with the constraints. So what those models often have in common is conditional independence assumption. So they have very important grounding assumption. It's the independence assumption. And we try to investigate what if we change the view on this problem? What if we get rid of those assumptions? And that's why we designed a basic model. So idea is very simple. It's two-stage architecture. We still have base model, the simple model that has independence assumption, and sequential model. So the base model, given some input, will just produce marginal probability for our classes. And sequential model, given those marginals, would produce full joint probability distribution for our combinations. And this way we have no independence assumption. So we tested these approaches with a few other competitors, like very simple base models that just has base model, and CCN that has this extra CCN layer that actually guarantees the constraint satisfaction. But those two, they have independence assumption. So, and our don't. Okay, so we did a lot of experiments, and I think the key advantages of using and get rid of this independence assumption is that we have, in general, greater capacity to learn the constraints implicitly from data. For example, comparing to base, we produce almost close to 0 violations. And we also have a benefit in performance. Like if we compare our performance with the CCN kind of very good approach that directly integrates constraints during the training, we see the huge improvement in terms of accuracy and of accuracy. That actually means that we are closer to the correct prediction because of our very expressive model. But because we focus on neurosymbolic AI, we focus on constraints, our main conclusion from our work so far is that more expressive probabilistic models can help to integrate the constraints. So that's only beginning of our very long line of research, because we want to see what this point of view can actually introduce, what implication it can also have. And we also plan to extend our approach to different types of constraints, for example, linear constraints in the real case, and also as our main idea and our main goal for now is to create a synthetic data generator that can have different hardness level of constraints, because for now, neurosymbolic AI, constraints are mostly used based on some domain knowledge without no control of the hardness. So, thank you.
Are there any questions from the audience? Nobody? So I shall ask a very simple question. Why have you decided to actually go this way to do your research?
Yeah, I'm actually very passionate about making. So I think the neurosymbolic AI is a great way to actually apply those technologies to practice, because you cannot just apply a neural network because it's actually black box, as was said here. You just want to ensure that you always produce something that doesn't violate the constraints and is meaningful in general.
Cool. Thank you very much. The next in line is Jirka Nedemlel from the Faculty of Science at Charles University, who is surely going to excite you with his passion for active inference. We recently had a breakfast together, and he was very passionate, so I hope that he will be able to exude this passion on the stage also.
Thank you. So my name is Jiří, and I'm coming from the same background as you, or some of you. I'm a technical person. I've studied technology and IT, and later I was more interested in AI and computational neuroscience. But I became an evolutionary biologist. So this is my pitch, and I would also like to join, invite you to join a seminar that I'm trying to create. It's about active inference, which is a new paradigm of AI. I will show the same invitation at the end of the presentation, and I'll tell a little bit more about it. So it's an invitation. My research idea that I'm working with is that basically evolution and intelligence is the same thing, plainly. And I will argue about that right now. So Darwin, he founded the evolutionary theory with the idea that there is a struggle, there is a competition between individuals of different species, or also individuals of the same species, for reproduction and survival. And only the fittest survive, and thus we evolve and adapt to the environment. So important idea here is that individuals who are competing. And Richard Dawkins, much later, another evolutionary biologist, said it's not maybe individuals, it's individual genes of our genomes that are competing for place in the genome. And they're trying to be the fittest and make the body the fittest so they can actually reproduce themselves. So it's a proposition that there's a different unit of reproduction. And you can go on and on with different units. You can think about demes, which are local communities that are actually relatives that are reproducing, and they are struggling together, helping each other. So sometimes you don't survive yourself, but your community will survive. And my idea here, it doesn't matter what unit you are looking at. It's all units that are all evolving at the same time. It's units within units. So this is one of the paradigms which is already common in biology. So it's not the individual's level. It's every part of the universe, every unit of the universe evolving at the same time. I will tell you about an anecdote, how people or human reasons. So human reasoning, for example, if you think about AI and its impact, so there's a lot of development in AI, and if you ask several people, what do you think will be the future of humanity, they can make several predictions, and they can say, okay, maybe there will be lost jobs, and there will be social unrest, we will be unhappy, etc. But what they will actually do will make small changes in their model, only a few changes, not like whole chain of interactions along the whole population and all the interactions that everybody has with everybody. So it's quite limited. But what evolution does is basically doing exactly what I said. It will make changes anywhere on the whole chain of interactions, anywhere on the population. It's not actually thinking, it's rather doing. And I'm arguing humans are better at doing also than thinking. Okay, breathe out. And why do they do that? It's because really the landscape of the world is intractable. It's really difficult to make changes anywhere at the same time parallelly. That's why we are adapting, and we are better at doing than actually thinking. We are better at finding the right prediction to survive in a complicated landscape, which is non-ergodic and which is non-convex. So it actually is difficult to find the optima, right? So the evolution is a parallel processing that could inspire how the reasoning should work in a parallel ways, in parallel agents that are doing anywhere on any unit some adaptations. You may also argue about the different goals of intelligence and life. So life should be reproducing and surviving. So its goal is reproductive, right? Every gene is trying to reproduce and survive, every individual also. And for example, a neural network who is predicting stock prices is not reproducing itself. But I'm arguing that my liver also is not reproducing itself. It's only supportive for the individual, for the collective organism. So you may see every part, every unit, not as reproducing itself, but being a supportive part that's actually helping a larger organism to survive and reproduce. So the same is intelligence, same is a neural network. And what is common there is basically trying to survive on a non-convex landscape, which has several minima. You can look at it as a loss landscape or an adaptive landscape in biology, where the peaks are actually the optimal. And what's the problem actually here? That you can get stuck in a smaller area of the possibilities options. Yeah. So you are limited by constraints, and how to get from it was already hinted in several presentations here. The active vision, active participation, and active inference is actually trying to adapt. It's a way how to adapt to different scenarios in different spaces, trying to palpate all around and finding the small changes that you can do on any part of the chain of interactions. And there are constraints, and these constraints actually not break or limit you from evolving. They do, but they also help you limit the number of options that you should search. So it's a search problem. If you would have one big optima, but there would be a lot of options, it would be really a never-ending search that you would go through. But thanks to the actual non-convex landscape, the evolution process is actually only looking in a smaller set of options. So my research is about optimization algorithms in evolution, about how to actually create constraints that find you the right optima. And we can talk about the same problems in neuroscience, in AI, and in evolution. So I invite you to conversate between biologists and data scientists, because we actually do deal with the same problems. And as I promised at the end, I invite you to join us a series of seminars. It's not a research group. We will basically be reading papers and trying to make it go into practice, because it's already a long tradition of active inference in the research based on the research of Carl Friston. So, thank you.
Thank you, Jirka. Is there a question from the audience? No question? Yeah, I know that I could count on you.
Yeah, really cool talk. And as you were talking, I was wondering about Carl Friston's work. So nice to link that. I guess just a thought that cropped up as you were showing the slide on the non-convex sort of parameter space that you're trying to optimize, and just thinking in the context of some of the work we heard from Joseph and others earlier about tasks involving robotics that are interacting with the world around them, and you could think of that parameter space as not only being very complex and non-convex and getting stuck in local minima and everything, but the fact that that parameter space is potentially time dependent and sort of changing, every second, every millisecond, or whatever it might be. And so you've got an extra degree of freedom potentially in your problem, and which makes it even more acute to find a good solution to that, because those sort of interactive models are going to have to be doing that continually.
Yeah, right. What's the question?
Oh no, I don't know if there was a question. It was just a thought, but really nice talk.
Yeah, thank you, Anna.
I have a question for you then. Why did you, after a promising career in data science, making a lot of money, you decided to switch to PhD?
It was very simple. I was also reading books, and I was stuck reading books about evolutionary biology all the time, and I wanted friends to talk about the topic, so I joined the doctorate, and I'm really happy now.
Okay, fantastic. Thank you so much. The next gentleman is Matyáš Veselý from the Faculty of Nuclear Sciences and Physical Engineering. Is he around? Yeah, he is. Fantastic. And he's going to talk about embedding-based subgroup discovery at scale.
Hello, everybody. So I would like to, thank you, present our findings on embedding-based subgroup discovery at scale. This research was conducted in collaboration with Workday Prague. So the motivation behind this research was to practically create a method which would be scalable up to hundreds of thousands of instances, like bigger data sets, and it would use recent advancements in representation learning, embedding creation, clustering, and then decision trees for the interpretability. So first, let me introduce you to the domain of subgroup discovery. So it is quite different from classification, which we all know. Pretty much in subgroup discovery, the task is to seek a set of readable rules that explain interesting pockets of data with respect to some target variable. As you can see on this picture, our approach as the UBA try to merge these ideas together, the ones I was explaining at the beginning. So the workflow goes like this. First, we make instance embeddings from tabular data sets. We use synthetic sentences created from feature value pairs. In our pipeline, there are multiple ways of obtaining these embeddings. Then we cluster these instances together to find candidate subgroups, which are then interpreted via decision trees, because in subgroup discovery, it's not enough to have just interesting subpopulations of data, that's just clustering, but you also need some way to interpret the data and know how to find this data, pretty much. So some membership rules are required. So far, this is our progress. This is a benchmark on mushroom dataset, a staple dataset in subgroup discovery domain, and you can see that our method has significantly shorter runtime compared to staple subgroup discovery algorithms such as VLSD or SDMap. So it is a meaningful trade-off with a bit higher memory usage, but significantly lower shorter runtime. This is benchmark with a different subgroup discovery algorithm, and you can see that resulting subgroups found by our method have the same quality metrics, which we use to determine their quality. The very important thing is to look at the overlap ratio and coverage. So there are two kinds of quality metrics. There are quality metrics on a scale of an individual subgroup, for example, the pick or rec. And then there are coverage and overlap, which are concerned with a list of subgroups, which are, for a practical usage, more important, because you want a list of subgroups to cover the whole data set and have a low overlap, which is our strong point. For practical usage, it's really important. Also, since our method is more scalable, we tried to run it on bigger data sets, 100 to 200,000 instances. But there we unfortunately were not able to compare with different methods, since they don't scale to these data sets. Some key lessons we have learned are, first, that embedding choice really matters, because for different tasks, different embedding methods are most useful. For most of the data sets we ran our algorithm on, word-to-vec embeddings were enough, but for more complicated data, transformer embeddings would be better. The second key finding is that sometimes it is hard to find clusters which have meaningfully different target distributions from the overall mean. So that's why we decided to incorporate something we called semi-supervised clustering, or target-informed biasing of the embeddings. And in the end, another interesting finding was that it is often hard to explain the given subgroup with a short description. So sometimes you need deeper trees to explain them. What are some future plans? So we would like to extend our package also for the regression style subgroup discovery, which looks quite promising. We need better calibration and stability studies to know how different hyperparameter choices affect our our results, and also domain validation with practitioners in the given field would be nice. And here comes my ask to you: if you know any big mixed type data sets which would be which could have some interesting subgroups in them, because it's not easy to find such data sets, since on the higher end that we're interested in, none other subgroup discovery methods have been ever tested. And that's all. Thank you for your attention.
Do you have any questions from the audience? No question? I have a question. No, Jirka, no question? Sorry, you were just trying to take a breath? Okay, you are allowed. I have a question for you. You've developed this research with Workday, a major US corporation that is also based in Prague. What are your key lessons and any recommendations you would give to young researchers who actually want to kind of bridge the two worlds and actually do something meaningful, and of course also obey the rules and principles of the corporate world?
Yeah, well, actually, the collaboration wasn't as easy as it may look. So pretty much, I just had consultant from Workday, but it was for me it was really meaningful, because I had the possibility to work on something real world, let's say, something that they are tackling every day at Workday, and the approaches were different, I think. Like the ideas that my consultant gave me were quite different from the ones that my supervisor was proposing.
So who was your favorite then, in the end?
Well, I'm not sure. Probably some language model, but both of them were super good.
Thank you. Great.
Yeah.
Any questions? No?
Question.
Fantastic. Oh, here we go.
What about data which are in real time changing your subgroup of?
Yeah, well, that would be also an interesting avenue, but for now, I don't think that any, not even our method is quite as quick to assess the data. So it's more like overnight maybe evaluation on the big data sets, but on like smaller data sets it's near real time, yes. Or it could work in this scenario, I think, for smaller data.
Okay. Thank you very much.
Thank you.
And the next gentleman is Mikhailo Mamchur from the AI department at the Lviv Polytechnic National University. He's going to share his insights on automating medical data processing.
Yes. Thank you. I'll make it quick. I know we're a little bit over time.
Take your time. 7 minutes.
Oh, nice. So yeah, at the AI department at Lviv Polytechnic National University, we love to collaborate with medical institutions, and sometimes we even get our hands on some real-world data, and sometimes it's even lots of that data. That way. Yeah. So the idea was to create a system that could take in raw, messy, unstructured medical data straight from doctors and independently and automatically turn it into structured data set that we can, as computer scientists, use to, for example, do segmentation. But after taking a look at the data that we get from doctors, we kind of identified the big challenge. This is like the structure that we could get sometimes. This is just 1 month's data. There's lots of different folders. Nothing is really structured. The naming isn't really like conventional. There aren't many patterns. This is the data for the heart X-ray of hearts. Not specifically brain data, sorry. And we use that for segmentation, but we found that there are lots of private or sensitive data marked on those, so we also needed to kind of handle that somehow. So of course, the solution would be to use the LLM AI agents. Here you can see like the graph. It's simple yet functional. What we do is we have a few nodes. The first one is to plan the tools. So an AI agent has access to all the tools that it needs, pretty much to really write data into a database. Then we have like a router node that will check if there are still any planned tool calls or no. And then if no, then we'll end it. If there aren't, we're just going to loop. So the system architecture really looks like that. So first we do data ingestion with AI agent. Then we do the filtering. So in this case, we wanted to do segmentations for heart vessels. So we filtered those scans using metadata-based information. Then we anonymized them, such as those X-ray scans that you've seen. Then we did some vessel segmentations using the deep SA model, which aren't ours, but really great research as well. This is an example of just raw data without anonymization. You can see that those details, such as namings and other like icons, they could really make a difference when using some of these segmentation models. And like the key results that we got is pretty much 85% of mapping accuracy. Might be cherry-picked, but for some of the months we got that. With some optimizations, we could get the cost of running an AI agent twice as low. Also, we got a huge speed increase by processing data in batches, such as splitting data into months. And since months are like isolated data, we could pretty much use agents on just months and run them in parallel. And we got good vessel segmentation quality. So that's it, yeah.
Any question from the audience?
Yeah, very nice work. I was struck by your use of the Hoff transform, which is sort of a nice, welcome, old school approach in this sort of world of all the AI. But you used it, I think, if I caught it correctly on the slide, for the problem of de-identifying images where you have burned in personal information on the image data. Is that right?
Yeah, we had this issue of different. It's not like particularly on the scans, but around the scans, and sometimes we could have different.
So the Hoff transform is, if I recall correctly from years back, this sort of sensitive to circles, and because your images, that's what you're interested in, you used it to extract just that middle,
just the masking,
area.
To specify like the dynamically kind of get the masking, because we had different X-rays from different doctors, and they aren't like specifically. We couldn't use just one mask.
Yeah, so you basically use that to retain the stuff in the circle and then suppress everything in the corners, which might have had somebody's name.
Exactly.
Okay.
Yeah.
Thank you very much. Thank you, Gabriel.
Thank you.
And the last but not least is Jana Vikliuk from the same department, who is going to share you her perspective on bridging the world of medical data and oncology.
Yeah. Hi, my name is Jana, as you see, and I'll talk about the analysis of medical data in the field of oncology. So let's move. Let's talk about the problem. Lung cancer is one of the leading causes of cancer deaths and worldwide. So every year, 2.5 million people has diagnosed with this disease, and approximately 1.8 million people dies from this. So the main reasons of that is late-stage diagnosis, comorbidities, and high rate of post-operative complications. So now we can move on to the research objectives. So our aim is to predict whether the person will have a post-operative pulmonary complications based on demographic, clinical, laboratory, and perioperative parameters. So as research is an iterable process, let's talk about the goals for the first iteration. So it's just the beginning of the research. So it is to evaluate the predictive potential of available data, to perform systematic benchmarking of multiple machine learning models, including classical models and ensemble models, for unbiased decision of which family is the most suitable for this task. So okay, let's talk about the data set. The data set was provided by the Lviv Regional Oncology Diagnostic and Treatment Center, which is one of the best in Ukraine, and the work was really complex oncology, I don't know how to say that, diseases. So the data set includes 460 records of patients and 52 features. It's clinical, demographical, laboratory, and perioperative parameters. So, and the target variable is, as I told, it's earlier is to say whether the patient with lung cancer will have post-operative pulmonary complications or not. So as you can see, it is a little bit imbalanced, and we must take this into account. So the data preprocessing was made. So the numeric variables were standardized, and one-hot encoding were made for categorical features. Also were detected and removed multicollinearity between different predictors, what might be not good for the model evaluation. So let's move on to the methodology. It's like to evaluate different models, and it is all classifiers, classical and ensemble, for unbiased decision, and it will use a stratified 5-fold cross-validation for more reliability, and because of the data is only has only 460 records, and as a metric was chosen rock auk due to the imbalance of the data. However, also important is recall. So let's move on to the results, and here you can see the curve for classical methods, and the other one is for ensemble models. So it's a bit better for classical models. However, if we take into the account other metrics on test and train sets, the variance is low, but bias is high. So classical models is too simple for this complex data. And what about ensemble models? This plot is worse than previous, but there it is due to overfitting, because on the train test results are really good. However, on the test sets it's really bad. So we need to decrease variance. So from there was we have K predictors. It was average from different top models, and it is a number of total free lung segments, total number of lung segments that was removed during the operation, and this free one is about is metrics about functionality of the lungs. So okay. From there we can have some key observations. So complex ensemble models have overfitting, and linear approaches are more generalizable. However, the next steps will be to balance the data set, to reduce class imbalance, to try apply clustering, and use cluster labels as new features, to calibrate ensemble models for variance reduction, and to explore explainability methods. So thank you.
Any questions from the audience? No? No questions? I have a question for you. What's next?
The next, we will, I think, to reduce variance to the complex models, like ensemble models, and then to play with balancing. I think we will try upsampling using SMOTE or ADASYN, and then we'll try clustering. And today I was inspired by one presentation to use autoencoder for this. So there is a lot of different ways, and we'll try to make the best result from this data, because it's really complex.
Thank you. Wonderful. Thank you so much. Okay, ladies and gentlemen, time for some break, about 10 minutes only. We have 2 more keynotes. So please refresh yourselves. There is a small poster session at the back, so make sure to check it out, no pun intended. And see you in 10 minutes. Ladies and gentlemen, I don't want to chase you away from food, but I have to, since we have an hour to go. So if you can finish your drinks and food, and you will continue in all these, there's going to be way more food, there's going to be beer, but unless you sit down and we finish the formal part, it's not going to happen. So if you can sit down for the next hour, and then there's going to be more time for networking. There's going to be more food and drinks in an hour. Please come and join us. Otherwise, you will disturb us. Cool. Thank you very much. So the next gents to be shaved, as we say in Czech, další pánové na holení. Roman and Anton Bushievs, you've heard a lot about twins. I have no idea who is who. And they are going to talk about their experience, actually about the virtues of international collaboration in interdisciplinary research. One works at CHIRC, one works at the Institute of Organic Chemistry and Biochemistry. Who is who?
Yeah, right. He's working at the Institute of...
Yeah. And welcome on stage, please.
Yes, thank you for the introduction. Yeah, so my name is Roman. We work on everything together with my brother Anton, but also with our amazing supervisors, Josef Šivec and also Tomáš Pluskal from another institute. Yeah, so we are going to talk about our experience with multidisciplinary research in international setting. So we are interested in machine learning applied to biology. More specifically, we are interested in discovering new molecules from nature using AI. Currently, if we try to estimate how many molecules from nature we have discovered so far, the estimate will be quite pessimistic. Basically, no one knows exact number, but estimates say that it's less than 10% or less than 1% or something like that. Why is it such a pressing issue? Well, because, for example, most of the currently prescribed drugs are somehow inspired or derived from molecules from plants, for example. Artemisinin is, for example, a Nobel Prize-winning anti-malarian drug, or paclitaxel is a famous anti-cancer agent, and so on. There are much more examples like that. So now an obvious question is, how do we discover these molecules from nature? Well, the most prominent technique is mass spectrometry. I'm briefly going to introduce the pipeline. So mass spectrometry starts with preparing some biological or environmental sample, which undergoes some wet lab preparation. After that, it is given to the mass spectrometry system, which is, roughly speaking, for each molecule present in the sample, produces some kind of descriptor of this molecule, which is known as mass spectrum, which somehow characterizes the molecule by fragments of molecular masses when the molecule is chopped into pieces. Then the goal is, of course, to decode this mass spectra back into molecular structures, which would ultimately lead to some scientific discoveries, such as discoveries of new drugs, for example. Unfortunately, currently the main bottleneck in this pipeline is exactly this step of decoding molecules from their mass spectra. It is known to be a very hard problem, both for human experts and state-of-the-art machine learning methods. So we believe if we can develop new, better AI to facilitate this step, we can really kind of significantly improve this discovery of new molecules from nature. So we need to develop better AI methods. So now let's think about ChatGPT for a moment. So all of you probably know that ChatGPT is extremely good, but what actually makes it so good? So it's a difficult question, but there are definitely two components that make it so good. So first, it's a huge neural network. And second, it's this huge neural network is trained on huge amounts of data from internet to predict masked words or fill in what is the next word in a sentence. So at some point, we started thinking, why don't we make something like ChatGPT, but in this domain of mass spectrometry? By that, I mean also a huge neural network, which would be trained on huge amounts of data. But in our case, not to predict missing words from sentences, but missing signals from mass spectra. Because the data is there, so there are public repositories of mass spectrometry data collected from all around the world. And we can also build a neural network for this purpose. So we build it, we call the neural network DREAMS. And if I were to summarize this neural network in one slide, this would be the slide. So basically, we made some kind of a pipeline that takes samples from nature as input and then combines wet lab, so mass spectrometry and AI technology, DREAMS, to produce some information about molecules present in the samples. So basically, we have this kind of AI plus wet lab pipeline that facilitates the discovery of new molecules. So, and we have tested this method in multiple case studies, and we continue to test it more. But now I want to focus only on one case study. So that is the discovery of new fluorinated metabolites using this neural network. So first of all, why fluorinated metabolites? So roughly 1/3 of currently prescribed drugs or currently used agrochemicals contain fluorine. So it seems to be important for molecules to contain fluorine. But if we now consider molecules from nature, we basically don't know almost any molecules containing fluorine, which is a big limitation, both from biological perspective or from the perspective of identifying new fluorinated molecules. So it's a challenging problem. That's why we decided to try to tackle it with our method. So this is the work together with our amazing colleague, Andrei Tekel. So he had this hypothesis. He had hypothesis about around 10 plants that can potentially contain fluorinated molecules. So he measured a lot of mass spectrometry data. It's hundreds of thousands potential mass spectra potential molecules. So and then we applied DREAMS to find this kind of needles in haystack, like molecules which contain fluorine. And in this way, we were able to identify a new family of fluorinated metabolites. So and for me, this use case is interesting because when I talk to biologists and I tell about these results, they often don't believe it because it's very rare for living organisms to produce fluorinated molecules. That's why I think it's interesting. In this case, AI really enables to find something like unique, interesting. Obviously, we are not the only group working on this discovery of new molecules. There are actually many labs around the world having the same goal to find some way to discover new molecules from nature. For example, if we now count the number of papers in this field over recent years, we can see that the field is exploding. We can clearly see this kind of exponential trend in the number of papers. So this is, of course, great, but it also comes with its problems. So the more papers are published, the harder it becomes to compare different methods between each other. It becomes harder to measure progress in the field, or people start reinventing the wheel, so publishing similar results. So we were thinking that the field needs some kind of standardization or some kind of unified platform to compare different methods between each other. For example, these two papers have the same idea, very similar idea, and then they try to develop some generative AI method to predict molecular structures from mass spectra, but it's extremely hard to compare them because they are evaluated on different data sets and trained on different data sets, so it's kind of a problem. So we really wanted to do something with it. Luckily, around the same time, there was a seminar in Germany, Dutch tool seminar, which is held every 2 years and brings together people from different research labs around the world, exactly with this goal to discuss how we can push the field forward. So it was a perfect opportunity for us to propose this initiation of standardized benchmark for AI. So over 1 week during the seminar, we brainstormed a lot how this benchmark should look like, so that everyone agrees that this discovery of molecules with AI will be fairly evaluated across different methods. And then we distributed the work and continued working remotely. So we made the MassSpecGym, which is a benchmark for AI to discover new molecules. So it has 3 main components. First component is that it's the largest public data set of mass spectra labeled with molecules. So people can train new AI methods on this data. Second, we also released the user-friendly code base to build, that facilitates building new AI methods. So, and also we rigorously defined 3 challenges in the evaluation metrics so people can consistently compare their methods between each other. And we also made the leaderboard to follow the progress in the field. So this initiative is actually a kind of worldwide project connecting 30 researchers in this field across 14 institutes. So mostly from the Europe, but also from the US and Canada. So this project was also presented at NeurIPS, which is a leading AI conference, which also increased kind of the impact or broadened its scope. So we were especially happy to see that many AI researchers who don't necessarily work on biology were kind of interested in our benchmark, as that they wanted to try out the new AI algorithms in the discovery of new molecules from nature. So as a result, in less than a year, we see that they were published at least 10 new AI methods, kind of evaluating the new AI algorithms on our benchmark. And we can clearly see the progress in the field. So each paper substantially increases the performance in these settings. So with that, I would like to finish my part. And now my brother Anton is going to continue. He will introduce a slightly different direction of our work. Hello, everyone. Yes, so my name is Anton. And Roman was just talking about the so-called small molecules. So you can think about 10 or 20 atoms. But in fact, if we get back to this image of a cell that Roman showed in the beginning, in fact, most of the cell's mass is given by so-called macromolecules or big molecules, so that we can see here on the slide. And particularly, I'm talking about proteins. So you can see 3 proteins highlighted here on the slide. So you can think of proteins as sort of mini robots that perform or like do all the machinery in our living cells. So they connect to other molecules, they transform them, and basically they what make us alive. As you can imagine from this picture, it's really important to understand the 3D structure of proteins. And actually, proteins have a quite special structure. So each protein is not just some random bunch of atoms connected together. So it's not just thousands of atoms connected together somehow in 3D, but actually proteins are sequences. So each protein is a sequence of certain building blocks, and these building blocks are called amino acids. And then when this sequence is produced in a living organism, it somehow falls into a 3D to obtain some 3D shape. So it's quite easy to get this sequence, so sequential information in a lab, but it turns out to be a really challenge to predict the 3D structure, or I mean to get somehow to resolve the 3D structure of the protein. Luckily, the company named DeepMind developed AlphaFold. And the AlphaFold is a neural network that does exactly this. It predicts 3D structures of proteins. So as you can see, the input to AlphaFold is a protein sequence, so a sequence of this this amino acid building blocks, and it predicts the exact 3D structure of the protein. As you may know, the leading authors of AlphaFold, Demis Hassabis and John Jumper from DeepMind, received a Nobel Prize last year for the development of AlphaFold. They received the Nobel Prize in chemistry. And obviously, AlphaFold is a major breakthrough in science, but actually it also struggles. So if you look at this example, we can see that, let's say, part of the protein is actually not predicted well. So we can see that the prediction confidence is very low, and the structure is not actually structured. So we can see that it's some kind of prediction noise. So you think, how can we actually improve this? How can we improve structure prediction in these challenging cases? So one insight is that all the structure prediction AI models, including AlphaFold, may actually be sort of too general. So what I mean by this is that we always have just a single big neural network to predict the structure of any input protein sequence. So whatever sequence we give to AlphaFold is guaranteed to give some solution. Sometimes the solution has lower confidence, sometimes higher. But do we actually need this generality? Maybe it's better to approach just one sequence at a time. So to address this, we developed the method which we call protein TTT, or protein test time training, that enables this so-called customization of AI models for proteins. And I'm not going to go into these technical details, so you may find more details in our recent preprint. And I just want to show the basic idea on a high level, which is actually quite simple. So we suggest to kind of decompose this problem in 2 steps. So instead of taking a structure prediction model and directly predicting the structure from the sequence, we suggest to do it in 2 steps. So first, we sort of tell the model, okay, take this sequence that we give you and think about it really carefully. So become a real expert just for one sequence, so without being general for all the proteins. And you may even potentially forget about all the other sequences. And so then, once the model becomes an expert, once the model becomes customized for just a single sequence, we tell it, okay, now you can predict the structure. So as you can see, the idea is really simple. So you're questioning, can it actually improve the structure prediction? So what are the most challenging, what are the most interesting scenarios where actually structure prediction doesn't work well? So luckily, this summer, together with Roman, we were visiting the group of Professor Martin Steiniger, who is now based in Seoul, at the Seoul National University. And Professor Steiniger is actually one of the authors of AlphaFold. During one of the lunches, we were talking to him about this problem. And he told us, basically, well, we are working on viral proteins, and they are really hard. So, in fact, the student in the group, Rachel Kim, constructed a database of predicted structure for all the viral proteins, of all the proteins in viruses. And in fact, only half of proteins actually predicted well by AlphaFold. So it's a really big challenge. So we can see some examples where the structures are not predicted well. So you're questioning, can we actually use our protein TTT method to improve this? So can we enhance our knowledge about viruses? And so just to give an example, so you maybe know how we have new variants of coronavirus all the time. And this is because viruses evolve very fast, so they mutate very fast. So basically, every time we deal with a new virus, it has different machinery inside. So it has different proteins, and so they are kind of different from what we know well. So to give one example, here we can see an entry from the UniProt database. So UniProt is a standard resource where we get all the knowledge about viruses. So normally, if you open this website and opens entry of some protein, we can see the name of the protein and its sequence and maybe even structure. And the function is often characterized very well, so we know that this part of the protein does this and that another part of the protein does that. But if we take this protein, so we can see everything we know about it is literally on the slide. So we can see that we don't know anything. So we only know the name of the protein. So we can see that it's some phage from which we can understand that it's a virus. So because phage is a virus that attacks bacteria. And then the only thing we know is the sequence of the protein. So why is this protein so mysterious? Actually, it has a good explanation because this protein actually comes from Antarctic ice-free soils, and it was sort of discovered during the first Latvian Antarctic expedition. So basically, this protein is very different from the proteins we know well. So now, quite expectedly, if we take some standard tools for structure prediction, such as different versions of AlphaFold or another popular model called ESMFold, developed in Facebook, so we can see that they actually don't work. So the confidence of the prediction is very low, and basically we see that the structures are not actually structured. So what if we now take ESM fold and apply our protein TTT approach? So in this case, we take ESM fold because it's very flexible and it's very easy to do this our strategy of customization. So we take ESM fold and just basically tell it, okay, just look at the sequence that we give you very carefully and just become an expert for just this single sequence and only after predict the structure. And what we can see is that if we only do 4 steps of this so-called customization, if we basically show the sequence 4 times to the model, it suddenly understands the sequence with nearly perfect confidence. So in this case, it really enables to predict the structure. So more systematically, we applied our approach to all the publicly available proteins from viruses. And we were able to improve the predicted structure for almost 70,000 viral proteins. This is roughly 20% of all the proteins in viruses that we know. So here we can see some examples where our method, so ESM fold combined with our protein TTT method improves, predict structures very well, but standard tools like AlphaFold and ESM fold actually struggle. So this is very exciting that we have these tools like AlphaFold that enable us to predict the structures of proteins. So it really enables us to understand better what's going on in living cells. But actually, the ultimate goal is not to simply understand what is going on, how the cells are functioning, but actually the ultimate goal is to somehow modulate their behavior or change their behavior. So what I mean by this is I want to illustrate in one specific example. So researchers, so scientists at the Dana-Farber Cancer Institute study this protein visualized here in blue. So this protein is called third telomerase. And it's actually a target against glioblastoma. So glioblastoma is an aggressive form of brain cancer. So what does this protein do in the brain cells? So actually what it does is that it repairs DNA of cancer. So we can see that DNA of cancer binds to this, attaches to this protein, and then it gets repaired by this protein in blue. So ideally, of course, we don't want the cancer DNA to be repaired. So ideally, we want to put some new molecule into a cell, such that it blocks the site. So ideally, we want to get this molecule in yellow, put it in the cell, so that it blocks the site and the cancer DNA doesn't get repaired. And actually, this molecule in yellow visualized here is what we got from our new generative model called broaden that we contributed to. So this project, broaden, is led by researchers at MIT, mostly Hannes Stark, and you can find details in the recent preprint. And so this model can generate this so-called binders or protein binding or attaching to other molecules. So we give it, for example, a protein, and then it generates another protein binding to it. Or we can also give it a small molecule or DNA, and then it generates new proteins or like so-called binders that attach to these molecules of interest. And as you can see, broaden is a diffusion model. So maybe you heard about diffusion models before in the context of image generation. So actually, what are diffusion models? So these models are based on quite a simple idea. So they're trained in the following way. So we take some real image and then noise it via the diffusion process. And then we train the model to denoise this, to remove the noise from images step by step. And it turns out to be very powerful, because then if we give a model, a trained model, a complete noise, and just ask it to denoise it step by step, then we get realistic images. So maybe you've heard before about Dny by OpenAI. So it's a diffusion generative model that can also be conditioned on text. So we can not only just ask it to generate something which looks like a realistic photo or image, but we can tell it generate us a teddy bears working on UAI research underwater with 90s technology. And actually, impressively, we can see that it is actually capable of generating something new, novel, which is maybe not present in training data. So broaden, as I mentioned, is also a diffusion generative model. But in this case, we don't condition the model, or we don't prompt the model with text, but we condition it with a molecule. So we give it some molecule in blue, and then we ask it to denoise or come up with some binder or some molecule that binds to the target one. And here, the concept of noise is also slightly different. So here, noise doesn't mean some changing of the colors of pixels, but it means the position of this binder and also its precise atomic configuration. for example, if we look here, so it's this denoising process, how the molecule is being generated. Here we can see that in the early steps of the model is denoising, or sort of figuring out where to put this binder, and only in later steps it's actually trying to come up with the best possible 3D shape of this binder. So now looking at this, you may tell us, so we have this nice animations on the computer, but actually, is it going to work the same in a cell? So if we produce, or can we even produce these molecules in real world? So in fact, this project is really amazing because the Boltzmann model was laboratory validated across 8 diverse campaigns and across 26 targets, or across 26 different molecules that have therapeutic potential. And this wouldn't be possible without this large team effort. As I mentioned before, this whole project was led by the amazing Hannes Stark and the team of computational people, primarily based at MIT, as well as a lot of collaborators who did this actual laboratory experiments to validate the designs. So at this point, I want to thank you very much for attention. And also say, feel free to reach out if you want to work together or collaborate. So with Roman, we really like working with other people. And we're actually looking for undergraduate students to work on some research projects with us. And I'm especially excited that there are many people from Ukraine today, because Roman and I are also Ukrainian. So let's meet and let's talk, and we would love working with you. Thank you.
Are there any questions from the audience? Yeah, fantastic. Anyway. I'll start with Matthias.
So I have one question for Roman and one for Anton. First of all, Roman, yeah, the first one, yeah, okay. Yeah, okay. White shirt, okay. So you said you trained pretty much transformer model on the
mass spectrum.
Yeah. Did you use encoder or decoder architecture?
Yeah, it's
decoder.
It's encoder only architecture, like birds from natural language.
Yes, because in ChatGPT is decoder only, but for example, I know that in image processing encoders are used, so you also used encoder.
Yeah, encoder only.
And did you maybe think about using decoder because it would maybe better fit your? I understand that the idea was to predict words, which it shouldn't know, but encoder has the whole attention with all of its parts, so maybe decoder would be better here.
Yeah, it's a good point. So first of all, we have some masking tokens. So even though it attends
so you have masking tokens.
Yeah, we have masking tokens. But also, I mean, I didn't show many kind of technical details about this mass spectrometry, but decoder only would have some kind of problems because in mass spectra there is a lot of noise. If we sequentially generate mass spectrum signal by signal, it would learn a lot of noise. So for us, it was better only to focus on encoder only and only to predict what was masked, and we know that it's not noise, for example.
Okay, so my question was essentially about the masks because it's the main difference with these two architectures.
Yeah,
okay, thank you very much.
Okay.
And I wanted to ask Anton, how is exactly the prediction confidence calculated?
So actually, I think it's really a genius idea that they came up with in DeepMind. So normally, even if you take like ChatGPT or like image generation models, they don't give you any prediction confidence. So they only give you like some text or some image, but they don't tell you how confident they are. And I think it's really genius about AlphaFold. It's also trained so in the way such that it gives you a structure and also a confidence. So in each part, it tells you how confident it is in each model, and it's just trained in a supervised way. So during training, you generate a prediction, and then you match it against the ground truth. You calculate some metric, and then you train another kind of module in this model just to predict how well it aligns with the ground truth. So.
Okay, thank you.
You were next here.
Yeah, great talk, and I loved the diffusion example at the end there. Fantastic. My question was a naive one, and I think you've partially answered it already. it was about the outputs of these models being how confident the model is that it's accurate or not. But my question was around, well, do you actually go and then check that against an actual experimental verification? So, in other words, is that confidence, is that a good proxy for accuracy if you go and experimentally verify?
Yeah, so how this whole field works of this de novo protein design with AI is that this AI is first asked to generate like thousands or tens of thousands or maybe hundreds of thousands of designs. So like really a lot. It may take like days or weeks on a computer. And then it's filtered using another maybe AI approaches. And then it's just, so the goal is just to reduce it, let's say, to 5 or 10 candidates that are just validated in the lab. So the goal is to optimize this in the way that if we only take 5, then we have some real hit that is going to work in a cell. And so actually Boltzgen is optimized very well for this. So in all of these case studies, maybe it takes, if you generate or if you reduce it to only 5 proteins, then actually at least one maybe like works in the wet lab experiments. So it's optimized very well for this purpose.
Thank you.
Thanks for the presentations. I was interested with the Boltzgen. How did the team assemble? How did you take part in the team?
Yeah, so this team is based at MIT, and actually I was supposed to go to have an internship there, but unfortunately due to some like visa delays, I was not able to go in the end. So I was just like Roman and I were just working online. It was very interesting because there is 7 hours time shift. So sometimes we were like talking in the evening here. So it was a very fun experience.
And what part did you exactly work on?
So I was working on the method, like on different aspects of this diffusion model and also how it is evaluated. Yeah.
So on the generative part?
Yes. Yeah. Cool. So this team consists maybe of, I'm sure exactly maybe 7 people who are working on the method. And then there are a lot of collaborators who are doing the actual wet lab experiments, like to validate the designs.
Any more questions? I have one last question, if there's no one else. Oh, there.
You study character of noise, for example, to shorten evaluation.
Sorry, what exactly do you mean?
You study character of noise to make prediction quicker? For example,
in the diffusion process.
Local noise of.
You mean in the diffusion process, right?
Yeah, in diffusion process, because there are some kinds of entropies, grained entropies.
Yeah, actually it's quite simple. It's a relatively standard diffusion. So we didn't do too much like experiments with this because it already works quite well. So if you just applies noise to 3D coordinates, so the concrete implementation comes from a quite standard diffusion paper from NVIDIA. So we didn't study like specific like types of noise.
My question is, what would be your one key piece of advice to any researcher wanting to do interdisciplinary research internationally, apart from going to cool workshops abroad where you can actually spark these collaborations? Is there anything else you would recommend?
I think maybe it applies to anything in life, but I just think to be close to good people. So I think Roman and I were very lucky to meet like our supervisors, Josef Šivec and Tomáš Pluskal. And I think it's just very fun, and we are also working on everything together. It's also super fun. So I think maybe it applies to anything in life, but I think just to like be around with like good people.
Cool. I suppose that's a just general life advice. Be around cool people. Thank you. Last but not least, and you should definitely wait for this talk, is a talk by Karolina Pštros. I was going to say Poljakova. She got married last year. I would like to say that as much as robots and biology and proteins and even AI may not be relevant to you all, what definitely should is that your research is actually being spoke about in a good, relevant way. And that's why we have Karolina here today. I met her 6 years ago when she just started working at the Artificial Intelligence Center. She was excited, but she kind of didn't know what to do with herself. And then she got really passionate about actually science communication. She decided to do a PhD. She went to Columbia University to broaden horizons. And I dare say that she's becoming one of the most kind of visible persons actually really in the Czech Republic in science communication. So thank you so much for coming. Thank you very much.
Ja, funguje. Tam. So, thank you for the invitation and the beautiful introduction. I'm really happy to be here today to talk about a topic that's really dear to my heart, and that is how we can communicate our research better in a way that's more transparent, responsible, and also engaging. As Lenka said, I'm the PR manager at the AI Center here at CTU, and I'm also doing PhD at Charles University, where I research science communication. I put up this slide to show you that I also understand you as researchers, and I know how crazy it is sometimes to be working for months or years on something only to summarize it in 2 sentences when media ask you or when you have to pitch something. I know it's really hard, and especially for research in AI, because we live in a world where when AI is everywhere, in headlines, in business, in sport, in marketing, basically everywhere, in memes, and sometimes it's not for the good reason. So I want to talk with you about how we can improve this whole ecosystem of communicating about AI, and also give you tips about how you can promote yourself better. So let's start with real headlines. In the first one, we see 5 ways to harness AI and end poverty forever. This is exciting, right? I hope one day we can accomplish that, but it sounds a bit like a fairy tale. On the other headline, we see that AI experts no longer saving for retirement because they assume AI will kill us all by then. So this is another extreme. It's a doomsday, and maybe the truth is somewhere in the middle. The problem is that these 2 narratives, someone laughed, so maybe someone's more leaning to this side, okay. The problem is that these are the 2 very extreme narratives. One is promising utopia, and another one is warning against apocalypse. So we have to balance this and talk about AI in a way that doesn't give in to the hype, but still gives hope. It's really important. Oh, sorry. One step back. Okay, I chose this second one because it mentions AI experts. This is a very common trick that journalists and other communicators do, that they mention the experts, scientists or specialist researchers, because it backs up any claim that you have in the headline, and then people care about it more, they trust it more, and this is why it's really important that we talk carefully and that we do not misuse this power that has been given to us as AI researchers on stage. We actually did a study about trust in scientists that was published in Nature. There was a big study of 70,000 respondents from 68 countries, including countries in Africa, Southeast Asia, Southern America, which is not very common because most of these studies done by Pew Research Center, Wellcome Global Monitor, or the Wissenschaftsbarometer are usually focused on Europe or America. So this was really like revolutionary in a way. And I don't want to go into the details, but basically the overall message is that people do trust scientists. There was a moderately high trust on a scale of 1 to 5. It was 3.62. This doesn't tell you anything, but we can talk about it later during the coffee break. But know this, you have the trust of public, of people, and as researchers, scientists, even as early career researchers, you have public on your side. And despite some populist claims of especially American politicians that there is a crisis of trust in science, it's not like that, and we still have some power in today's world, and that's why we have to take it responsibly. So you may ask if there are any ways that we can foster this trust and build it further. Luckily, there are, and it's not some plain marketing tricks. It's actually good communication habits that you can take with you to your workday, but also everyday life, hopefully. So let's start with the first one, science fairs. This is a very good place where you can meet people, even younger generations, and get them excited for your field. When kids and even adults can touch science, when they can do an experiment, when they can interact with it, it's really powerful and it goes a long way. Because when you connect science to that emotion, it stays in their minds, it goes longer way because there is some emotional connection with it. So going to these things is really impactful. I like this tweet by Matt Blaze, who's a computer scientist. When people say the reason you can't trust science is that scientists used to say one thing that turned out to be wrong, but now say a different thing. They are actually explaining why science works so well. You're scientists, so you know that this is what science is, but the general public doesn't know this, and it's really important to be repeating this. The methods of science, how the system of science works, why it changes, why it evolves, because unless we explain this, people are not going to understand why things can change and they still remain true. This picture is here because of the concept of ivory tower. You may have heard about it, that scientists are sometimes perceived as people in their ivory towers, isolated, looking down on people, being very distant from everyday life, in their fancy lab coats, very unapproachable. We know that this is not true, but not everyone behaves that way, and sometimes scientists maybe do not present themselves in a way that invites dialogue. So I really encourage you to step out of these ivory towers, go to places where people normally are. So if you want to make an impact on kids, go to the places where they normally appear, in schools, for example. If you want to have impact on politicians, go where they are. Because if you keep inviting people to universities, it may not always work, because to some, universities are a place of bad memories or fear, or they don't have the education, so they don't feel encouraged to go there. So that's why events like Pint of Science, science cafes, public experiments, and these things work, because you go to people, to your audience, where they are. This organ is the second most important for scientists, apart from brain, and it's because it causes listening. So I really encourage you to not only talk when you do science communication, but also to listen. It's something that we forget, and it's actually really important in building trust, because oftentimes people don't need to hear information. They've heard so many times that smoking is bad for you, and they still smoke, because sometimes it's not just about knowing the information, it's about other barriers that they have to overcome. And if you are looking down upon them for not knowing something or not changing their behavior according to science, you may just not have enough information yourself for why they behave that way. This shrug emoji describes probably also another important aspect of science, and that is saying, I don't know. If you appear on media and you are asked a question that you don't know the answer to, don't worry and say, I don't know. Sometimes researchers feel pressured into responding, but it's so much better to say that you have no fucking idea, because it's honest, it's transparent, and it doesn't create misinformation. You can also recommend other experts, your friends from the field, that can answer those questions. And last but not least, trust is being built by representation and inclusion. So if you see people who look like you talk about science, it's more powerful than if you see someone who's totally different. One example is the WHO, the World Health Organization. In their missions in Africa and elsewhere, they often collaborate with community leaders, including religious leaders, to spread information about science. So they may work with local priests who can persuade the community there to be vaccinated, because they are trusted characters in that particular group. And this is really important also if you come from underrepresented group, either women in science or a certain minority. So if you are in these groups, I encourage you to step up, because it can go a long way if someone who looks like you, thinks like you, comes from the same group, hears it coming from you. So now we know how to improve trust in scientists, but you may still ask, why should I care? Maybe I don't want to communicate about science. Maybe I just want to be publishing my research and let it speak for itself. Well, for one, communication increases your visibility. So it can bring you funding opportunities, networking opportunities, and maybe also some career development. It may sound too abstract or far-fetched, but think about this. When you finish your PhD and you will want to go for a postdoc, you contact some professor, you send your CV, and even with a stunning list of publications, there may be other candidates like yourself. We've seen today on this stage that there's so many brilliant researchers, and if they all apply for the same job, you might not have anything extra to offer them. And if you show that you care about the impact of your research on society, that you go do public talks, that you have some experience commenting the current events in media, this can bring like an added value to you as a candidate. And we can ask the senior researchers here, but they value this extra work, these extracurricular activities, and it also makes you a better trained speaker about the science that you actually do. Another reason to communicate science is public understanding, like I talked about vaccines during time of crisis, then inspiring the next generation of researchers. You are young AI researchers, so you may not worry about what comes next. But once you have your own research group or you work at a company or have your own startup, you need to have candidates that come from your field and that are brilliant. And unless you inspire the next generation, you're not going to have that pool of candidates. And last but not least, social responsibility. It's a common argument mentioned when we talk about science communication that science is funded from public money, also private, but also from taxpayers' money. So we owe it to the public to be transparent about what happens with the money and how they can adopt the research to make their lives better. And if this didn't persuade you, let me tell you this. There are thousands of scientific papers published every day. How do you want to make real impact? Even if you did science communication just to improve your public speaking skills or to attract other scientists to collaborate with you, it is worth it. So you don't only have to worry about the public, but about impact in the academic community. Am I good on time? Okay. So let's talk together how to choose the right channel, because when you decide to communicate, it may feel quite overwhelming. There's podcasts, there's university websites, there's public debates, there's all these options, including some alternative ones like forums on Reddit where you can actually present your research. So how to decide on where to go? First, think about what you want to achieve. So what's your goal? Maybe you don't have that clarified yet, but maybe you already settled on inspiring other generations or finding collaborators or changing people's behavior or persuading them to make decisions based on your health research, for example. So this is very important. Then think about who the target audience is and which channels they use, because you don't want to publish a bunch of TikToks if you want to influence a political decisions, because there may not this target group may not be on that specific social network. Also think about what your communication strengths are and how much time you can dedicate to creating content. Sometimes researchers feel pressured into going on a platform that's very trendy or to do public talking because that's what's said to make the most impact. But if that's not your thing and you feel sweaty and uncomfortable and you love to express yourself in writing, just do that. It's really better to be impactful and spend the time in the medium and format where you feel like you belong and it's natural to you and you don't mind spending time on it than pushing yourself over the boundaries. Of course, it's good to try new things, but don't overdo it and really enjoy what you like doing already. So some content ideas, because it's not only about publishing about promoting your latest research. You can of course do that. You can summarize a research paper, but you can also show the behind the scenes, the process of how science is made. This goes back to the method and the process of science that I was talking about. We need to show the public how science is made, how research is evaluated, what does the peer review process mean, etc. You can also share a surprising insight from your field. It doesn't always have to be about your own research, your own project. You learn many papers every week. You listen to podcasts. You can take these ideas, summarize them, publish them, not as a research paper, but on social media, for example, and basically use the knowledge that you gain through studying in your promotion as well. You can also share the personal struggles and lessons, again, to show that scientists are also human beings, bust myths in your field, or connect current events to your research. Science journalist Pavla Hubalkova, who was here last year, did like a science recap during a World Hockey Championship 2 years ago, I think, because you can find science everywhere. So connect it to your field, and if there's a, I don't know, Taylor Swift concert, just figure out how you can connect this event to what you do, because there's always a way. You can announce a career milestone, I'll talk about that in a bit, and invite collaborations. So when you think content, don't only wait until you have your paper published. Talk about the process and talk about your whole field to gain audience and to show them that you're an expert in that area. Okay. So let me show you one example. When you want to post something on LinkedIn, for example, or other social media, you might be pressured into saying something like, happy to share our new Nature paper, great collaboration with the team. The happy to share has become like a motto of annoying communication on LinkedIn already. And everyone does it. And I think I have many posts like that because it's just something that you see happening and you do the same thing. But it has no added value to the audience. If you just announce that you're happy and you're sharing something, well, why would I bother reading further? You should always start with something like a hook, something exciting, something that tells the audience if they're the right ones to read the message further. So for example, some immunotherapies fail in 60% of patients. Our new study shows how tumor cells create immune deserts and 3 ways to overcome this. This is just an example. Of course, you will use your own research, but this is to show you that you should be specific and you should be thinking about the audience first, what they might need to know, what is their interest, their struggles, their fears, and address those. So don't just announce that you did something, frame it in a way that's relevant to everyone else. And the last section of my presentation is about how to avoid hype, because it's good to hype everything you do, but maybe it's not always for the best. So let's break it down. Try not to use hype or over-promises. Especially in AI research, this is very common. Even when something is improved by 2%, they call it groundbreaking or revolutionary, and then the audience just roll their eyes because every time they see something related to AI, they feel like it's another hype and they don't want to read that. So try to be as specific as possible and also talk about what the model or algorithm or whatever doesn't do. Be transparent and honest, because that creates credibility. And I know this is hard, but try not to personify AI. We shouldn't say that models think or want or understand. We should always be more technical about that. They detect patterns, they predict outcomes, they I'm not an AI researcher, you know what the models do, but try to frame it in a way that doesn't create fear or a doomsday, because this is really important. And now I'm sure your grandparents are maybe afraid of AI and tell you these scenarios about the world ending because they think that the AI is some entity that's capable of making its own decisions. Maybe an example, if I'm very bad at examples, so I prepared one and now I forgot it, but let me think. Yeah, if you, instead of saying AI understands sarcasm, say for example, our model can classify sarcastic tweets in 80% accuracy. See the difference? So try not to personify. Don't hide uncertainty. So if there are any things that are uncertain, unclear, if there's any biases in the data or unpredictable outputs, talk about it, share it. It can help you connect with other researchers to solve that issue. And again, it creates honesty, transparency, and trust in science. Don't use misleading visuals. So we've all seen those glowing brains or robotic hand touching a human one, which is actually something that I had on my social media a while ago. So I'm one of you with this mistake if you're doing it too, because they oversimplify and also reinforce the hype. And I don't know how you, but every time I see an article about AI, they seem to have the same cover photos, so it doesn't even differentiate them. So think about maybe the social context that your AI is used in and use that instead. Or use real diagrams, but don't put them in the header of the article because no one just understands it and it's not good. It doesn't attract eyeballs. So please use something with emotion, something that's specific, but something that's not misleading like this. You can also use pictures of the process of science. You can use a picture of yourself in the field or your team or the experimental setup, you know, anything real that shows how that science is made. And don't skip the wider AI context. This is something that we often forget, but if you talk about the outcomes of your research and where the technology is set in beyond your research, it again poses you as an expert on that thing, and it shows that you're transparent because you understand that it can have also negative implications. I will not go into detail in here, but these are some sources that I would recommend if you want to learn about science communication further. Maybe one to mention is Quest, which is an EU-funded project that publishes toolkits and guidelines and articles about how to improve your skills. There's also many booklets. When you Google, you will find tons, and a lot of it is really good because some of these guidelines in communication are very old and we just forgot to use them when it comes to AI or science communication for some reason. So I encourage you to go back to them. And words of encouragement, just get started, because I know how hard it is to get on stage. I personally am not a fan of that, but I try to do that because I know that you will not improve unless you do it. And the world doesn't need perfect science communicators. It needs authentic scientists who speak, who are honest, who are transparent, and who want to engage with the public in a way that makes the AI research impactful and used by most people as possible. That's it. Thank you very much. Connect, chat with me after. I'm happy to talk.
Thank you so much, Carolina. There's a good question. I had tons of questions, but you answered them already. You mentioned saying my model classified instead of my model understands. How do you ensure that the audience will not stop reading at classified?
Well, again, it depends on the audience. If you talk to other researchers, I'm sure they will be more inclined to learn about technical language and they will know exactly what you mean. Maybe there's a whole different way to talk about this that's more engaging. Maybe you can talk about the impact it has or the problem it solves or how you did something, why you made these decisions. Yeah, it depends on that specific use. But I understand that sometimes when you want to be precise, it can become overly technical and really annoying to read further. But for example, in news media, in news outlets, you often have like main information, the general message, and then as you read the article further, it goes into more detail. So it's not like a scientific paper that really like structures it one after another. It has a different hierarchy, and it starts with what everyone needs to know, and then go into more details. So maybe leave the details for later. Yeah.
Okay, thank you very much. Any more questions? I still have a question. Okay, Martin.
So a follow-up for the question. So like my kind of understanding was that maybe the wording "my model understands something" might be plausible, might be okay if I kind of evaluate what kind of impact that might have. Like especially if I'm talking to a broader audience. Do you see it like that, or would you just steer away from that?
It was just an example, so I'm definitely not saying that you cannot ever say it. It was more in the lines of overly personifying AI, because...
Sure, but I'm also talking in general. Like, maybe sometimes if I kind of think about it in detail, and sometimes even the personification might be okay. Like, if the impact isn't, like, catastrophic.
Yeah, I don't have data to say like the exact impact each of the statement has. So this is more experience, but I would be cautious. Unlike in other fields where you're encouraged to use metaphors and analogies and make the research come alive, with AI, I think we have to be much more careful because of all the doomsday scenarios and because of how the public misunderstands so much about AI.
Anybody else? I have one last question related to working with journalists, with media. I think many researchers are horrified with the idea that their research or whatever they say might be misinterpreted for the kind of clickbait headlines. So what would be your key advice to give to a young researcher who might be approached, who might be suggested by his university to actually give an interview or something along those lines?
So a few things. Always try to work with the press officer at your institution, because they usually know how the media ecosystem works. They have built relationships with the journalists, and they can kind of shield you in front of against the evil journalists, so to say. But from my experience, most of the journalists working in Czech Republic on scientific topic are very understanding and nice, and unlike in, for example, political journalism, in science journalism, they usually work with the scientists. They authorize the text, which is not typical at all in other domains. They check whether the terminology is okay, and they are very, how to say it, very, I would say nice. Like they're nice to work with. The problem is that sometimes the editor changes the headline right before publishing because they want to attract more people and pay for their website running. So even when you are okay with the journalist, there might be a higher power that affects this. But in online media, sometimes they're okay with changing the headline after that. But another good tip is to propose a really good headline yourself. If you are preparing an article for a medium where they ask you to do the text yourself, it's not like an interview. If you have a really cool, catchy headline that's accurate, they will use it. But if you say something that doesn't create any emotion, that doesn't move the people, that's not very specific, they're gonna change it. And also, like, media is not the only platform. If you are so afraid of communicating with journalists, you think they're part of the establishment and they just want to ruin AI scientists, I don't think that, but maybe you do. Just use other channels that you can control completely. Start your own blog, speak on podcasts, work on, contribute to a university website where it's internal medium, it's not owned by a media house. So there are different ways. But I understand this fear, and myself, I had bad experiences in the past. But once you get to working with the journalists, you create a flow, and maybe you can like hijack the system by providing your own ideas for the headlines.
Fantastic. Thank you so much.
Thank you.
Last but not least, I'd like to welcome Vít Dočkal back on stage so he can very briefly introduce the CLARA Young Innovator Award 2026.
Of course, science is motivation, competition is motivation as well, and money as well. So, hello everyone again. Let's watch. So that's it. Actually, we are announcing today the CLARA Young Innovator Award. For you, we have great ideas, you know, in your mind, and great future ahead of you. And maybe let's speak about that. We've got small presentation, very short, very brief. So, next year, there will be winners. That will be announced on May 2026. And this is exactly for you. So if you have innovations which could help aged population, aged people, with your fantastic digital technologies, AI, etc., please apply. You still have a lot of time to do so. Next slide, please. Because the submission deadline is March 15 next year, and we will notify the winners in April, and the award ceremony would be held during the International Prague Health Summit in actually May 21st and 22nd. And actually, it's a great opportunity to you to go even further with your ideas, further to the market. Because once you get this award, it's not only some money, it's also visibility, connection, outreach, and impact. And what we all actually want to do is to help our patients, you know, the aged population. Those are in need. And actually, this is CLARA mission to actually bring your innovations to the market. So where to start? With you guys, you know, with your young generation. So next slide, please. Small award, good motivation may be enough for just thinking about that. But I don't know if you actually saw the presentations of all CLARA Days, as this is part of it. But if you don't, you can see it, actually, because it was all streamed and it's recorded, so you can see it on YouTube. Actually, there were superstars here in Prague. And some of them are still with us, right, Adam? This is the guy from, you know, GE Healthcare Global, you know? The man, he's beyond the imaging program at GE Healthcare. Just came from Boston, you know? You can have a beer with him, you know? And there were other superstars, you know, and these guys are ready to help you. You know, with their connections, with their expertise, etc. So please, do not hesitate. Just go, scan that QR code, go for the submission, and be a winner. Because it will not be a help only to you and your team, but at the end, it will be a help for our patients and clients, you know. Maybe it's all. Do we have another slide? Yeah, we need to thank our sponsors. And actually, I started these CLARA Days with statement that we are celebrating the science and innovation. What's the metaphor for that? Well, robotic bar. So let's celebrate the science innovation all together, just right there at the corner with our fantastic robotic bar. But before we do so, I wish I could help those who are invisible here, but actually are so needed this even could happen. So let me please welcome here, personally, Eva Doležalová. Are you here? Evie. This wonderful lady actually is a miracle. Thank you. And you can stay here, of course, you know. But, you know, even such a miracle Wonder Woman as Eva couldn't do it alone. And we have a wonderful list of people which helped us together, right?
Mm-hmm. Very much.
Yeah. I don't need to use the list because I have it in my mind, but just for the record.
I will control you.
You, of course. I think the second one woman here is in the room is Terka. Terka, where are you? Good. Well, of course, this is CTU guys, you know, great, excellent team, but there are also other organizations like INDRC helping you. Pavlina, maybe you are handling these flowers, but one of is for you. Thank you very much. And I'm happy to thank Lenka. She's so wonderful as well, you know. Thank you for your collaboration. Thank you.
Thank you.
The flower is there, you know.
Thank you very much.
Thank you. Thank you
Thank
very
you.
much. Thank you. By accident, only women, you know. Actually, so the flowers are very appropriate. But you know, if we want to do such an event, we need money, you know. And those folks who are taking care about the treasury are important as well. So let me please welcome here Petra Mikeshova. She's securing all the funds, you know, not only for Rike, for everything, you know. Petty, hello. But such complex event need
Another woman.
a lot of women, of course, but a lot of resources. And I'm very happy to welcome in Lenka Kadeřábková as well, as another part of the package, you know, paying for his wonderful event as well. And this is now I'm in a conflict of interest actually, but I would like to thank my wife. That she actually was that patient, you know, with a little boy, just 1.5 years old, to survive this week, you know. And Eva, please, the one flowers is for you. And I'm a lucky man because I can have a picture with these wonderful ladies, you know. Would you mind that I stay in the middle, Eva?
This is not gender balance. Are you okay with it?
Yes, I'm okay.
Thank you very much. Thank you.
So, and it's over. I mean, the official part, and then we can go on, you know, with a beer. And it's, maybe, Lenka, you have a program.
Just one last thing. Thank you so much. Thank you so much for coming and staying till the very formal end. Please, one big final round of applause for all the speakers. I've got high hopes when it comes to presentation skills and young research talent. So please, once again. Thanks so much to all the partners, long names, you will remember them all. And just one organizational things. Those who have actually completed the application form, you might have ticked some of the topics you might be interested in discussing over beers. It's a bit of a hide and seek endeavor, but they are actually little A4 papers with the topics. The grand goal of these papers is to actually help you concentrate around those little signs. So you can go for that. Remember that there is The refreshment part is actually next door, but hopefully these will help you to find people that are interested in the same topic, or just kind of be proactive, open, and you might find them over good food and beer next door. So thank you so much to everybody, and have a great rest of your evening. Oh, and one last thing.
Sorry, I'm very not used to speak to the microphone, but it's my pleasure to also thank Wiet for we know that without him as well would this not happen. So thank you so much.
Thank you, Lenka. I'm very happy that we survived this week with a very complex, very rich agenda, and of course we owe many thanks to all who contributed. It's not only this team, but it's really wide team. The ladies in the cold at the registration desk, come on, it was quite a cold, chilly, and we have bottles for them, to get warmer. So ladies, thank you, and it's Helena. Where are you? Come on, Annette, come on, Veronica, come on, just here. We have bottles for you because you were very chilly. Do we have bottles? Can I have one package for Helen? Yeah. So that's actually Silvaner for you to. I know it was very chilly over there, right? Yes, thank you. Yes, and thank you very much as well. Thank you very much. Annette, are you here? Oh, okay. Duties. So it's for her. She's still working, but Annette, come on. You laughed because I was just saying that it was very chilly at the registration desk, so maybe this make you warm. Thank you. Okay. Thank you. And a big applause for these ladies. They really risk their health, for our event. So thank you. And now, party time. Do we have some music over there? Yeah. Thank you. Food is over there, just across the corridor there, so you can have a food, grab a beer, enjoy.
you.